Welcome and thank you for standing by. At this time, all attendees are in a listen-only mode until the question and answer period. This webinar is being recorded and may be posted publicly. If you have any objections, you may disconnect at this time. Now I'd like to turn the webinar over to Erica Yu. Erica, you may begin.
Thank you. Good morning. Welcome to the session. My name is Erica, and I'm going to be your moderator for the next hour and 25 minutes. As you may have seen on the program, this session is going to be a bit different. These are all projects in progress, which means we are pulling back the curtain to focus on the methodology and the process of getting the research done. So you're going to see some finished results here, but really the focus is on the process. One of my favorite parts of FedCASIC has always been the community coming together to learn from each other. And the presenters in this session are bravely sharing ongoing projects and opening themselves up for us to, poke around the hood, see what's going on. I've asked each of them to highlight the obstacles that they are facing as they conduct their research and areas where audience contributions would be welcome. So for those of you in the audience who are already doing similar research, we hope that you will contribute to the discussion on how to overcome obstacles or ideas for next steps. And then for those of you in the audience who are maybe not quite at that step, but interested in doing similar research, we hope that this discussion helps you get started. So to that end, our session format is going to be a bit different too. We're going to be taking Q&A for each presenter immediately after their presentation. So audience, as your questions come to you during the presentation, please type them into the WebEx chat because we're going to be going through the Q&A immediately after the presenter finishes. If you put them into the chat, I'll read the questions out loud. If you want to ask it directly, you can raise your hand and we can get you unmuted. So with that, let's get started. First, we have Kristen, who's a behavioral scientist at NCHS. Kristen, go ahead, take it away.
Okay, great. And I'm unmuted, correct? All right, great. Well, hi, everybody. I am from the Collaborating Center for Questionnaire Design and Evaluation Research at NCHS. A quick thank you to Erica for organizing this session and to everyone who's helped put it together. So yes, I'm at NCHS where we apply cognitive interviewing and mixed methods approaches to inform our question evaluation and design work. And I'm just a quick shout out to my co-authors, Zachary Smith, who's been co-leading this project with me, Ben Rogers and Travis Hoppy, who are our fantastic data scientists. So if you have super techie questions, I may refer you to one of them. I'm one of the more subject matter experts. And then we also have Valerie Ryan and Paul Scanlon. Just a quick overview here. So I'll start out with some quick background and context. I will then describe our approach to evaluating the model that we've developed, present some results of our most recent phase of evaluation, and then I'll conclude with how the model can actually be accessed. So you yourself can use SANS. It is publicly available, and just go through some tips and guidance, based on our experience. So as with many things, our work with OpenText began in the context of the pandemic. We were not able to make use of our in-depth cognitive interviews initially, so we began to explore collecting open text through our web survey to help inform, to supplement our question evaluation research. The value of open text in survey research has long been recognized, but there are certainly challenges as well. There are, higher burden on respondents, and of course, data quality concerns. There's also time and cost factors, which for us, as with many of you, may have, long since hindered the use of open text data. But as we all know, ever rapidly evolving advances in data science are making it possible for us to explore new tools to tackle many of these challenges associated with open text, including the detection of poor quality or item non-response. So prior work trying to detect item non-response. more about just, what is item non-response? So more than just the presence or absence of data for an otherwise responding unit, the issue of item non-response is more nuanced for open-ended questions. And researchers have thought about this in a variety of ways, using different terms to refer to productive versus non-productive, or useful versus not useful, sincere versus insincere types of answers. But ultimately, we have found that what constitutes item non-response or a useful response depends on the research question and is ultimately a subjective judgment best made by the researcher. So looking at prior work to try to detect item non-response, prior work has included rule-based approaches, such as a tool called eval-answer. And there are also machine learning approaches more recently, such as Young and Fernandez, who have used bag of words to detect invalid responses for a study on autobiographical memory. There are definitely limitations of this prior work. So we had discovered eval-answer first and ran it on some of our data. We found that it was very limited because it was based entirely on rules or regular expressions. So it tended to miss particular phrases that weren't necessarily captured by a rule, like I don't know or no clue. It also flagged otherwise valid responses that may have included, expressions of uncertainty. And then in terms of other NLP methods, specifically bag of words, this approach tends to work best on lengthier and cleaner open text, while in our experience, survey open text responses are often short and can be quite messy. These bag of words approaches also tend to require a project-specific training set. So our approach also involves using natural language processing, but it involves the use of a bidirectional transformer for language understanding, or BERT model, using SimCSE, a pre-trained language model. The model was developed using massive amounts of data scraped from the internet. These models are powerful because they understand language as opposed to relying on a set of preset rules or word frequencies. We have further trained the model with targeted human coding in a process called active learning, which I'll talk a little bit more about. And thus our semi-automated non-response detector for survey data, or SANS, was born. So we have developed the following taxonomy to identify different types of item non-response. So we have, of course, a complete non-response, which is like a blank text box, gibberish, don't knows, or other expressions of uncertainty, refusals, this other category, which we call other or high risk, which is kind of a catch-all category for responses that tend to be shorter, low quality responses, but they tend to be like at risk. This is the category where oftentimes there's a judgment call that has to be made about whether or not that response is useful or not for the research. And then, of course, versus a valid answer. So the way that the model works is that the model assigns a score 0 to 1 for the extent to which a open-ended response falls into each of these item non-response categories, plus a dominant score, so the category with the highest score. So a little bit about our process for training and refining the model. So our initial training set was a sample of 3,200 responses from 6 different web probes that we've used on our research and development survey. So at the end of round 1, we had good consistency with most of those categories, but less consistency overall between valid versus any of the other item non-response categories. We were also getting good results for identifying item non-response, but the model was flagging more valid responses as item non-response than we felt comfortable with. So in a subsequent round, we had 2 coders review and arbitrate the results to retrain the model. And following that round of training, we really saw improvement in the model's ability to correctly identify valid responses. So a little bit about the data. So the data we've drawn on to develop and evaluate SANS has come from our research and development survey. So during the pandemic, we repurposed the survey as the RANDS during COVID-19 surveys. Some of these rounds were supplemented by non-probability DINATA data. And then our further evaluation work, which I'm going to talk about most today, has drawn on more recent rounds of RANDs, but again, all of which have been conducted using NORC's AmeriSpeak probability panel. So this shows an overview of the model development and evaluation process. So I just want to illustrate here these arrows that go back and forth. So phase 1, which was based on 2 probes as case studies, resulted in changes and refinements to the model. So that's why there are those kind of back and forth arrows. Phase 2 assesses model performance using 4 web probes as case studies. So just really quickly, because this has been many stages, the results of phases 1 and 2, along with phases 3, 4, and 5, have been the focus of previous conference presentations and are also the focus of a forthcoming paper in the Social Science Computer Review. We just got, final acceptance of the paper, so it should be available quite soon. Today, I'm going to summarize the results of those various steps of evaluation, but I'm going to focus here on phase 6, which is our most recent work. So just looking at the results of our evaluation so far. So in phase 1, we found overall that the model was doing well at identifying true valids and slightly less well identifying, true or what humans would identify as non-response. So high specificity and good sensitivity, and I'm going to talk a little bit more about those metrics in a minute. What we found is that this resulted in a manageable set of model-identified non-response that could then be hand-reviewed by the researcher. There were a couple of outstanding issues with non-responses that kind of slipped through our training. There was a probe in our training set where none was sort of a valid answer, but we felt like in general that should be, that should be flagged as a refusal. And then secondly, we had questions about how well the model would hold up on non-COVID or health-related topics since the data had been trained on COVID and health-related topics. So we retrained the model and carried out our phase 2. And we found again that the model was doing well at identifying true valids and slightly less well identifying true item non-response. The issue with none was resolved, but we did see some slightly weakened performance on a probe related to religion, so completely different topic. Just quickly, in phase 3, some analysis that we did to examine the model for bias related to key sociodemographic subgroups revealed no notable evidence of bias. In phases 4 and 5, in general, we found that SANS detected item non-response with more nuance than simple rule-based approaches based on word count and time latency. So in phase 6, we have focused on evaluating SANS on medium length and other specify open ends, because these are other types of open text that are often used in survey research. And on an ever-increasing range of topics. So we had some health topics, but we also had questions on disability, gender identity, firearms, etc. So I'm gonna, to get to the results, I'm gonna walk you through the results for one of our case study probes, just to sort of help you understand our process. So this question, sex education, we were doing some work with the National Survey of Family Growth. So we had the survey question, which is the first bullet. So, interested in knowing about what type of formal sex education you may have had. And then the probe here, what kind of instruction on how to say no to sex were you thinking about in the previous question? That's our open-ended question. So to illustrate the approach we used, again, to evaluate all of our case study probes, the 2x2 that you see here has the results of human review on top and the model results along the side. So looking at where we agreed with the model, we have the upper left cell. Oh, looks like my animations may not be working. Oh, there we go.
Kristen, we've just got a minute or so left in your presentation time.
Oh my goodness. Okay, wow, sorry. I'm going to go through this much more quickly then. So I will just say that the key takeaway here is that we had lower sensitivity and very, very high specificity, so that the model was doing a good job identifying true valids, so valids that humans also thought were valid, and slightly less well identifying item non-response. So there's always a trade-off here, but we think, so the model in general, this is the pattern that we saw with many of our other results, is that the model may over-identify item non-response, but in that way, the model is identifying responses that can easily be reviewed by humans to then make that judgment call about which responses should be included in the analysis. So here's some results from our other medium length probes. You can see that, SANS really continued to hold up, good rates of sensitivity, typically higher rates of specificity. And then we have the results of our open ends, which again cover a wide range of topics. We have smaller numbers here, but again, SANS seems to hold up pretty well across many of these different topics. Some slightly weakened results for like religion and gender and sexual identity. So that may warrant further exploration. So overall, we're seeing, that SANS performs, really well, identifying a data set of likely valids. It has continued to hold up with these shorter types of open response texts. And then just getting into model access, SANS is currently available on Hugging Face, and there's a model card which offers examples. Some knowledge of Python is needed to run SANS. However, we are, working on trying to make it, executable directly through R. So stay tuned for that. We do have some detailed guidance and best practice. I won't go through these because I'm running short on time, but these are, written up in more detail in the paper that I was talking about in the Social Science Computer Review. So if you're interested, I can definitely share that with you. I'll just say that looking, next steps, we look forward to understanding more about the generalizability of SANS to, again, like further topics, other types of data, and other languages. So far, we've used SANS in English. It was trained, predominantly on English language text. So we're interested in exploring, but it may require, developing SANS based on, other large language models that are developed using other languages as their base. In general, we're still examining, now that we have this ability to more effectively manage some of our open text, how is, this open text data valuable to us in terms of that, informing our question evaluation and design research. And then in the big picture, one thing that we're really interested in with the rise of open AI is can we in our SANS 2.0 give SANS more information on the context or like topic area of a probe that would improve its performance even more. And I will end here with just some resources to some of our publicly available resources, and my email. Please feel free to be in touch if you have questions. I look forward to the Q&A. Thank you.
Thank you, Kristen. That was a lot of information. It's sorry to make you jam it into such a short time.
It's always a challenge.
Go ahead and put them in the chat or raise your hand. We've only got a minute or two of question time. I'll take moderator privilege and ask you a question that I was wondering while I was listening to your presentation. I know you mentioned that it's really context specific, really project specific, but it seems like the step of reviewing the set of responses to come up with that taxonomy would be really labor intensive. Would you advise against maybe starting with a generic set or using the set that you used? Is that something that would not get you good results?
Yeah, I mean, so like, are you talking about like if you wanted to use SANS yourself, or if you wanted to kind of, okay, so SANS does use that taxonomy that I, spelled out. So all your results will divide your results into those different categories, and then you would receive a dominant score. So, whatever. So then if you sorted your results, you would get like the refusals, what SANS thought were the refusals, what SANS thought were the expressions of uncertainty, et cetera. I think it is kind of context specific. So for example, if, depending on how your question is constructed, if none or, none of these is a valid response, you would need to look into that refusals category, right? Because, the way that we've kind of set up the model, those types of responses are going to get flagged as non-response because for the most part, none is not a valid response to most open-ended questions. You know what I mean?
Yeah. Yeah.
So yeah, I think, you know, again, our model is called the semi-automated. So we really, you know, need to, you know, it would be great if it was just out of the box. You could just run the thing and use your data, but you know, it's not like that, you know, but we have found that it does improve the efficiency greatly, you know, because SANS does a really pretty good job, you know, of identifying that first pass. And then if you've got that set of likely non-responses, you can go through them so quickly and make that quick judgment call. You know, do we actually
Spend
want
your
these
time
answers
there.
or not?
Right. Well, thank you very much, Kristen. We now have our next presenter coming up. We have Hanyu Sun, who is a principal survey methodologist at Westat. Hanyu, do you want to go ahead and start sharing? Great, take it away. Hanyu, if you're talking, I can't hear you.
Can you hear me all right?
Yes, great.
Okay, great. Sorry about that. Good morning. Yeah, so today I'll be providing an overview of the machine learning audio pipeline that we developed at Westat to facilitate interview monitoring and question assessment. So first, I'd like to acknowledge my collaborators, Tinyan and Anil Batalahali, for their contribution to the project. So computer-assisted recorded interviewing, or CARI, has long been used by survey organizations to monitor interview performance and assess survey questions. So CARI produce question-level audio recordings that capture the interactions between the interviewer and the respondent. Interview monitoring often aims to detect interviewer falsification and undesirable behaviors. Question assessment often aims to identify survey questions that may introduce measurement error. So to use CARI, a human coder needs to first listen to the audio recordings of the interaction between the interviewer and the respondent, and then evaluate and code features of the question and answer sequence using a pre-specified coding scheme. So for example, with interview monitoring, the coding scheme can be designed to identify interview falsification by asking coders to indicate how likely the interviewer fabricate the whole or part of the interview. In addition, coders are asked to assess how closely the interviewer followed the standardized interviewing protocol. So such as whether the interviewer read the question verbatim and whether the interviewer probed in a non-leading way. So coding of question level recordings of the question answer sequence can then be further aggregated to provide respondent level or interviewer level evaluations. And interviewers who are identified to have deviated substantially from standardized interviewing protocol are called out for intervention, for example, retraining, etc. So although it is a very effective tool, this conventional coding of CARI tends to be label intensive and time consuming. So as a result, in practice, only a small proportion of completed interviews or a selected group of key questions are selected for coding and evaluation in a timely manner due to resource constraints. So what do we mean by saying a question answer sequence? So in a standardized interviews, the interviewer and the respondent follow the paradigmatic question and answer sequence. So interviewers are expected to start by asking the survey question verbatim, and respondents are expected to reply with an adequate response. Sometimes interviewers end the sequence in a third conversational term by acknowledging the respondent's answer. So the audio pipeline processes audio recordings at the question answer sequence level. So in this example, there are 3 turns, including 2 turns from the interviewer and 1 turn from the respondent. The interviewer asks a question at the first turn, and the respondent provided answer immediately at the second turn. And then the interviewer acknowledged the respondent's answer by saying thank you at the third turn. So at Westat, we developed a machine learning audio pipeline to process and analyze audio recordings of survey interviews in real time with low cost. So the pipeline is used to identify and sample interviews with a high risk of being falsified. interviewers exhibiting undesirable behaviors, and survey questions with poor performance and prone to response error. Excuse me. So the pipeline includes three component processes built on pre-trained machine learning models: speech diarization, speech tags, and acoustic feature extraction. So the speaker diarization process determines number of speakers and produce conversational turn level metrics, such as number of turns and turn durations. The speech tags process transcribe conversations at turn level and produce metrics to evaluate interviewer question rating behaviors. And the acoustic feature extraction process produce acoustic parameters at the turn level to predict responding emotions. I'll provide more information in the following slides. So these metrics are then informed, all the metrics are informed by survey methodology literature and are designed to facilitate quality control at three different levels: interviewers, respondents, and survey questions. And the projects can choose which level to monitor based on their specific quality control needs. So in addition, the pipeline has an optional sampling process that can select interviewers, cases, or survey questions for conventional carrier coding. So next, I'll provide some additional information about each of the three processes in the pipeline. So we'll start with the speech diarization process. So this process uses piano pre-trained models to determine who spoke at which turn in a question-answer sequence. So at the end of diarization process, the number of different speakers is output for each question level audio recordings. Since the pragmatic question-answer sequence, it was only two speakers, assuming interviewer and respondents. Recordings that are detected to have 0 or only one speaker are automatically flagged by the pipeline to be at a risk of interview falsification. So this process also produces other turn-level measures, such as the number of interview turns, number of respondent turns, turn duration, etc. And then the second process is the speech tags, and that's where we use the OpenAI Whisper pre-trained models to transcribe conversations at turn level. So the pipeline subsequently compares the turn level transcript to the exact question wording from the survey instrument to produce distance measures on lexical and semantic similarities. And we use OCR text recognition to extract the exact question wording from the blast screenshots so that audio files such as response name, address are being captured correctly. And then we use that as a reference text to compare with the transcript to produce the distance measures. And the pipeline uses distance measures to evaluate interviewer question rating behaviors. So a large distance measure suggests that interviewers are more likely to not rate question exactly as worded. And interviewers with large distance scores will be automatically flagged as showing undesirable question rating behaviors. Sorry. And then finally, the acoustic feature extraction process. That's where we utilize the offline batch mode of OpenSmile to extract the extended Geneva and minimalist acoustic parameter sets. So that set includes, I believe, 88 different measures about acoustic features such as pitch, jitter, shimmer, loudness, and so on. We then train models to predict emotions such as the respondent being confused by this acoustic measure parameters using human coding results from conventional carrier coding. So in the conventional carrier coding, we regularly ask coders to code the extent the respondent had difficulty understanding and answering a survey question. So we use human coded results to train, test, and validate the emotion models. Next, I'll provide a high-level overview about how the pipeline produce metrics can be used to monitor interview performance and to evaluate survey questions. So regarding interview, so one thing I want to make it very clear is the pipeline is really we view it as a screening tools to make the human coders activity, their behavior, like their coding activities more efficient and effectively. So we're not replacing human coders. Human coders plays a very important role in the entire process, as I presented earlier on in the flowchart. So speaking about how to utilize the pipeline metrics to facilitate interview monitoring as well as question assessment. What we do is, for example, start with interview performance. The pipeline produce flags to rank cases and interviewers. So if the it flags recordings with 0 or only 1 speaker as high risk of falsification, it uses the distance scores to determine whether the interviewer read the question verbatim and whether the interviewer maintained the question meaning. So then the results are the results at question and the sequence level, and then it being aggregated case and interview level to prioritize coding in the conventional carry system. So meaning we're using the priority flags produced by the pipeline to determine which case to be coded at first in conventional carry system. The pipeline also has an optional sampling component, as presented early on, that can be used to select a number of cases or interviewers to be human coded in conventional carry coding. For example, the top 10 worst case of the day to be human reviewed in the conventional carry system. And then regarding question assessment, the pipeline produced flags to rank survey questions on set performance measures based on survey methodology literatures. So as I stated early on, a paradigmatic question answer sequence is composed of one turn by the interviewer who's supposed to read the question verbatim, and one turn from the respondent who's supposed to provide an adequate response. So any departure from the paradigmatic sequence indicates that they are problems with the question answer sequence, the process, and speaking to probably poor performance of the survey question. So for example, question inducing more than one respondent turn suggests that respondents are likely to have asked for clarification, asked for repeat, or expressed uncertainty with answers. So the more respondent turns in a survey item induced, the more problematic the survey item is. Similarly, question invoking more than one interviewer term indicate that interviewer likes to have reread the question, probe for clarity, or provided definition or clarification, and so on. So the more interviewer turns, the higher chance that the question performs poorly. And another example is long pauses. So a long pause after the interviewer finished asking a question and before the respondent first turn speaks to difficulty the respondent may have had with answering that particular survey question. So all these measures are then, they all start with question and the sequence level, and then all the measures being aggregated to survey question level to rank their performance. And similarly, such results can be used to prioritize or sample survey questions for the conventional carry coding. Here's a list of items for discussion. So first, we observed that quantity of audio recording affects the performance of the pipeline. So such as background noise, overlapping speech, and far field effects, meaning often what we notice is recording the interviewer, we use the speaker from laptop, so interviewers sat very close to the speaker and their voice was very clear, but then sometimes the respondents sat far away from the laptop. Their voice being captured, but not as clearly as the interviewer's voice. And subsequently, we have some questions for discussion. So for example, okay, if we know the quantity of audio recording affects the performance of pipeline, what can we do with that? So how can we identify audio recordings of poor quantity before send pipeline for processing? And how to account for the quantity of audio recording during the pipeline processing? Can we account for that metrics or that feature about maybe we'll have a rating about quantity of the audio recordings and then take that into account while processing audio recording and generate the flags? And also, could that be an interviewer training issues? Can we work with the interviewers so to make sure they get a clear recording of the respondent speech? So that's some question for open discussion. And then secondly, how to best utilize human coded results from conventional carry coding to improve the performance of the pipeline. So currently we're working on, as I mentioned earlier on, using human coded results to train, test, and validate models associated with emotions. So I wonder if other speakers audience have thoughts on how to utilize human coding results to improve the pipeline performance. And then finally, as a different question, is how to introduce the pipeline to new users or stakeholders about what it can and cannot achieve. So for example, the goal of the pipeline is not to replace human coders. Instead, it is to make the human coders work more effectively and efficiently. so resources can be allocated to review cases that are most likely to be problematic. And I'm curious how other presenters deal with those issues. That's it. Thank you.
Thank you. If you wouldn't mind going back to your discussion slide so we can
Sure.
stew on those a little bit longer. Thanks for doing that. Yeah. We've got a couple of questions in the chat. To my very naive eye, they look similar. So I'm going to read them both to you at the same time. Curtis Chapman is wondering, what kind of embeddings did you use to compare Jacquard's similarity and cosine distance of the speech transcriptions? And Monica Puerto is wondering, for your cosine stroke Jacquard distance, what were the calculations based on? Maybe embeddings from an LLM model.
So what we did is we get embeddings from, well, I felt I'm not the right person to answer all the tech questions. I can get response for you, but I know for the semantic measures, we're looking at word embeddings. We try different metrics and different classification models. And what we do is, I think we tried maybe 5-6 different ways, different distance scores to measure for the lexical and as well as semantic distance measures. And then we did some human validation about the results to say how closely they agree with the human coded results. Like if one of human coded review, for example, I listen to recording and code it. So that's how that helps us to determine among all different 5 or 6 different distance measures we looked at which one to use as in the current pipeline. And also, let me see, what's the other question? Yeah, and for how do we, we use piano, but the question is how, well, I have to say piano sometimes is very fuzzy. One thing we notice is no matter which distance measure you use, if the quality of the audio recording is not very good, you're not going to get a very very accurate detection about voice activities. And that just mess up with the turn, determine the number of turns you have. And once you mess up with the number of turns, then it just adversely affects the following measures you have. So if the recording is very clear, we have some like mock interviews, we make recordings in a lab, in the office, it's very clear. In that sense, the distance measures performs very well. But then once you're adding in actual data collection, sometimes you have a very bad recording quantities that definitely just make the recording, the performance of pipeline not very optimistic, not very good in that way. So that's why I have a question here saying, so knowing those recording quantity would affect performance, what can we do with the quantity of the recordings? So currently we're thinking about training a model. Actually, for the human coding part, we added a question to the conventional carrier coding, ask the human coder to evaluate the quality of the audio recordings. The idea will be probably we can train model to use the acoustic metrics we grabbed from OpenSmell to put the recordings into different like acceptable quality, good or bad quantities, and count that factor into the procedural. But that is ongoing right now, but that's just one thought.
No thoughts about changing the interview setup to prevent the garbage from coming in the first place? Is that impossible?
So that's an interview training question as well, but sometimes what happens with especially in-person data collection is very hard to control. Maybe the response in a rush, and interviewers try their very best to get hold of the response. So yeah.
Okay, we have a couple of more questions in the chat. I'm going to actually ask you, Hanyu, to respond to those in the chat because we're out of discussion time. We're going to move on to our next participant. So everybody, if you're interested, take a look at the chat while we're getting set up for our next presenter. Our next presenter is Jerry Timbrook, who's a research survey methodologist at RTI. Hi, Jerry. I can see that you are starting to share. Yep, looks good. Take it away. And unmute yourself.
Hear me now?
Yes, perfect.
All right. Hi, everyone. Thank you so much for the opportunity to chat with you today. I want to give major kudos to whoever handled the order of the presentations because I think Hanyu did a lot of the heavy lifting on the background for our presentation as well. So I'm gonna just build on that a little bit. So that way I don't have to spend as much time on those parts. But on behalf of my co-authors, Kirsty Weitzel and Peter Baumgartner, I'm really excited to talk to you today about a small piece of RTI's pipeline that Hanyu was just talking about from on the Westat side. We're focusing more on the unit level interviewer falsification piece. And ours is this small piece of it. The things that we're looking at today really are a work in progress in the spirit of this session. So we have some preliminary results and some ideas for things that we're going to do in the future. And we're really excited to hear what the audience and other panelists think. So as we've been talking about interviewer administered surveys, we have some expectations for administering a standardized instrument. Most importantly, we want our interviewers to conduct a genuine interview, no unit level falsification, because that can compromise data quality. We want them to read the consent statements exactly as worded to get around compliance issues. We need to ask each applicable question in the instrument and read those questions exactly as they're worded in the questionnaire. Just make sure that all respondents are receiving the same question wording, making sure that we're reducing interviewer effects on measurement. And so again, we all have these pipelines that kind of evaluate the different steps of the interview process to ensure that our interviewers are doing what they're supposed to be when they're going out into the field or they're making a phone call to respondents. The focus of this presentation is a new way for detecting unit level falsification that's a little different from what's been done in the past. So thinking about a paradigmatic interview, as Hanyu said, we traditionally have two speakers, an interviewer and a respondent, and deviations from this two-speaker paradigm can potentially affect data quality. If we have fewer than two speakers, meaning we don't have both an interviewer and a respondent, that's a big flag for falsification. But it could also mean some potential technical errors in interview equipment. We were talking about recordings not being high enough quality to pick up on the voices of other people. So it could be pointing to technical errors as well. Greater than two speakers could be indicating the potential presence of third parties. If you think about the respondent's partner, a child, a parent, and there's a lot of literature to say that third parties can affect respondents' answering behavior. So it might be helpful to know how many people there are in the room, just to see if that adds some additional context to the answers that are being given by a respondent. The work that we're focusing on today really hones in on the fewer than two speakers, potentially falsified curbstoned interviews. So that's what we're taking a look at here. The traditional tried and true way of determining the number of speakers in an interview is manual review. Typically, we listen to a random subsample of interviews rather than all of them, around 10% or so, and have QA staff listen in and see if there are indeed an interviewer and a respondent on those recordings. And then we note the number of unique voices present. We review all of that, and it can make it expensive and time consuming because you got to train your QA staff. They have to use time to actually listen to each of those interviews. And we also have this idea of naive sampling of cases. Since we're not always listening to 100% of the recordings, we don't know the quality of the random 10% subsample. So something that a lot of us, including Hanyu and other researchers, have been investigating is there a better way? Can machine learning help us be more efficient in our selection of cases? So prioritizing cases that that QA folks may want to review at a higher priority because machine learning has indicated that there could be a problem. So a potential approach that Hanyu just went over, speaker diarization. So here you're pulling apart conversational turns that each interview actor utters in a recording. So you're identifying when in a recording each actor speaks, and that allows for an educated guess at the number of speakers. So that's kind of the pipeline that Hanyu was just talking about. This does take a lot of processing time, and it requires an extra step to map speakers' identities to conversational turns. And it's also agnostic to the expected number of speakers. So it's just pulling apart what it thinks is the right number of speakers. We're not giving it any sort of prior to say, We expect 2 speakers. Can you tell us if the actual recording deviates from that expectation? So our approach focuses in on that assumption about the number of speakers, and we use what we're calling speaker count verification, an approach that reduces processing time by starting with the assumption that there are n speakers, 2 for our purposes here in this particular case, so an interviewer and a respondent. The steps of the speaker count verification process, I'm going to go into each of these and with a little more detail here in a second. We identify the portions of audio recordings with actual speech, calculate speech embeddings, we do some dimensional reduction, we cluster our embeddings, and then we calculate cosine similarity. So let's talk a little bit more about those. So again, we start by identifying portions of our audio recording with actual speech using Celerio voice activity detection. And this is great because it does a very good job of figuring out what parts of a recording are speech and what are just loud noises that aren't speech. So we use that to figure out, okay, where do we actually have speech in the recording? And then we move on to calculating our speech embeddings using SpeechBrain, which is an open source all-in-one conversational AI toolkit. It basically means that we represent the speech identified in the previous step as a vector. Then we move on to dimension reduction. So we had a lot of dimensions of these embeddings. So we use t-SNE to reduce the number of dimensions here, which basically just says we're taking high dimensional data and giving it a location in a 2 or 3 dimensional map. And once we've done our dimensional reduction, we cluster. So we are telling the clustering algorithm that we expect 2 speakers. So there should be 2 distinct clusters of embeddings. And there are lots of different clustering algorithms you could use. The 2 that we investigated that we'll talk about today, k-means agglomerative. And we also identify the speech embedding that is closest to the center centroid. So that's the stars that you see right here. This is what we would consider the center. So once we have that identified, we calculate cosine similarity, where higher scores mean more similarity, meaning that if a cosine similarity score is pretty high, that means there's a good indication that there's only 1 speaker. So if cosine similarity of speech embeddings closest to the cluster centroids are greater than 0.25, so you're thinking about the distance between these 2 here, we're going to flag that particular recording as 1 speaker. And this 0.25 is the cutoff that's used by SpeechBrain. So pros here, it allows us to assert that 2 voices are present, enabling a meaningful test of cosine similarity across clusters. Some cons here, it's generally uninvestigated in this context to our knowledge, so there could be a lot of cons that we don't know about. So we investigated this in 2 different ways. The first is with a single state CADI study about health. We had full and partial interview recordings for this. There were English and some Spanish interviews. And the nice thing about these recordings is that they're previously reviewed by human QC staff, and all were verified to have at least 2 voices. So we know that we're starting with a data set that has 2 voices just to see how things are working with our different approaches. So let's talk about some results using the 2 different clustering algorithms that I mentioned in our previous slide. So the first is agglomerative. It's counting 2 voices for the vast majority of the cases, but it's saying that there's 1 voice, meaning a cosine similarity greater than 0.25 for 103 cases, which is about 11%. So not ideal. That's a lot of what we might consider to be false positives. We also took a look at k-means, and we see a similar percentage of cases that are incorrectly identified as 1 voice when all of these cases should have been identified as 2 voices. In looking at the paper that Hanyu was talking about in her last presentation, they found something really similar when they were looking at carry field recordings as well. There was a high number of 2 voice recordings that were incorrectly identified as 1 voice recordings. So their number was around 31%, and that was just based on my calculation from the table in Hanyu's paper. But we're lucky enough to have Hanyu here, so hopefully in the chat she can talk with us a little bit about that too. So this isn't something that's necessarily rare depending on what approach you're taking, but we're not improving to the point of perfection beyond the diarization model. And I would also point out that Hanyu's paper uses carrier recordings of field interviews, and these are CADI interviews, and it's possible that the CADI recording quality is a little bit better than what you would see in a field interview. So it's not quite an apples to apples comparison here either. And also, interestingly, these two algorithms didn't identify the same cases as being one speaker cases incorrectly. So they identified 37 recordings where both of the methods agreed that they were one speaker when they should have been two. But there were 66 agglomerative and 62 k-means that were unique. So that means that these methods, while the percentage of cases that are being incorrectly identified are similar, the actual cases that are being prioritized or pointed to is different. So we thought that was really interesting and worth discussion today. So now that we've looked at the two-speaker recording, we also wanted to do a look at one-speaker recording. So we wanted to see how well do these methods do whenever we're looking at just one speaker in a recording that could be potentially falsified. So we didn't have any of those cases on hand from the data that we had available to us. So we actually took interview transcripts for 6 randomly selected cases. And we had one man and one woman read 3 cases each, recording just themselves. So they read the transcript of the interview, and they read through both the interviewer and the respondent part. So there is one person, one voice using the exact same text that was used for actual interview recordings. So here we found that when we took those 6 actual interview recordings, we got 100% correct detection. The algorithm identified all 6 of those as having 2 voices. But then when we had it take a look at the female voice only, so this is a woman who is reading and she is the only person on the recording, it correctly identified having one voice 100% of the time. However, it didn't do as well with the male voice only. It only said that there was one voice for one of the 3 recordings and incorrectly identified 2 of them as having 2 voices. So we wondered maybe the person was doing a fake voice, pretending that when they read the interviewer part, maybe their voice was artificially higher, or they made the respondent's voice artificially lower. But when we listened to the recording, it was pretty steady that it was the same vocal characteristics when that one person was reading it. So definitely some tweaking to do there, some next steps to think about. Speaking of next steps, there's a lot of things that we could do to try to improve this work in process. We could take a look at varying cosine similarity thresholds, could try additional clustering methods, review calculation and reduction of embeddings, and investigate more than 2 voices. We've only looked at 2 voices right now, and again, we know that having additional folks in the room can affect answering behavior. And during our conversation, we'd love to know what ideas you might have. And just a general point for audience discussion, we'd like to know, what have been the main pain points when applying machine learning technologies to real-world data in your lives, even if it's not about interviewer falsification? What have you tried? What are your lessons learned? And maybe this was just a common theme that comes up in our conversations today. So thank you all very much, and we're looking forward to the discussion.
Thank you. Yes, so if you've got questions for Jerry, please put them in the chat and we'll read those out loud for you and we'll answer them in our Q&A time now. Yes, this reminds me of when I read aloud to my kid and I try to do different voices, because of course when you're listening,
Exactly.
It's very different than reading. You don't get the same cues. But I don't know, maybe a crazy question. With these models, would you be able to sort of feed extra like a priori information about the interviewer, like have them record them saying something, so then you're like, okay, I know for certain this is the interviewer, and have that help the model figure it out? Is that a possibility?
So that is something that if we became involved earlier in the process would be a potential. But for this particular project, we got the data once the study was already done. So we weren't involved from the beginning. It was something that we came in on the back end. But that's not to say that we couldn't start a project that way and maybe have them read through the questionnaire once by themselves without anyone else on there. And that way we could get a good idea of what their cluster looks like, more or less. So yeah, that's an interesting idea, Erica.
I mean, good luck getting the interviewers to do that, but that'd be neat. And then
Yeah.
I was,
And I just wanted to know, Hanyu did mention in the chat that they used both mock interviews and production interviews. And the production interviews, correct me if I'm wrong, Hanyu, were face-to-face. They were actually sitting with the respondent versus our study, which was CADI. And there could be differences in the quality between those two use cases. And it could be, so it's not quite an apples to apples comparison when it comes to accuracy. I think we would say that field interviews probably have worse recording quality than telephone, just depending on where someone is sitting, how many kids are running around in the background, that sort of thing.
I don't know if Hanya wants to jump in, but I mean, I have heard of some analyses of CADI where you have like different audio streams. I guess you guys didn't have that with your data file, where the way that the CADI Center records it is you have one audio stream incoming from the interviewer's device, and then another audio stream. So it's sort of separated for you. That's not a possibility?
That is not something that we had, but that is really interesting to think about. Writing that down. Yeah, I don't know that we have that ability, but what we receive, it's all
one file.
one channel.
Yeah.
But that doesn't mean that that's not happening somewhere in the process and that we could try that as well. That's another great idea.
All right. Hanyu, did you want to jump in? Did you have any thoughts in reaction to what we were learning from Jerry's work about anything that relates to yours?
Sure, I would say I agree with Jerry about the CADI and actual face-to-face interaction audio recording quality will be very different from each other. We tried, that's why we tried mock interviews and we tried field production recordings. And even in the mock interview setting, we tried to vary the background noise with very different features we know from literature that will affect the performance of diarization. And it just confirmed, yes, we have background, we have a podcast playing in the background. The diarization process won't be very accurate as compared to a very clear recorded conversation between interviewer and respondent. So I felt the next issue, an interesting question is how to, as I mentioned in my presentation, how can we evaluate recording quality beforehand, before processing the data, so we get more accurate response. But also for my presentation is accuracy, of course, that matters and performance matters, but we really more about, as I emphasize, is a screening tools. So the problem we're facing in the production is we have hundreds of recordings, thousands of recordings coming on a daily basis. How can we process them in a very quickly way to identify maybe like 100 out that 1,000, they probably at a high risk of problems with the interview respondents. So we want to pass that to human coders to validate. But once you have human coding results, you can refine the model you have, get more insights from that. But yeah.
Hanyu, you also mentioned something that we're running into as well, which is the idea of communicating what you're talking about, to stakeholders.
Right.
And when you say, it's difficult for us to evaluate your face-to-face recordings when you don't have a microphone that is actually picking up what even the interviewer is saying. They think that machine learning is just kind of a magic answer that can pull all of this information out of a recording where it doesn't actually have an interviewer or a respondent voice. So we have to actually have them listen to the recording and say, okay, as a human being, can you hear what the interviewer and the respondent are saying? And then, when they say no, you have to say, great, then neither can the algorithm. So there's a little bit of stakeholder education as well. So what you're saying really resonates with us as well, Hanyu, as we've been working on our own pipeline. That it's just the old adage that it's junk in and junk out. So you really want to start with high quality interview recordings, and maybe that changes the way that we think about our CADI and our CAPI technology going into the field.
Thanks for the discussion, guys. I'm going to move us along. We've got our next speaker. We have Victoria Narayan from the Bureau of Labor Statistics. She's a research statistician in the Office of Survey Methods Research. Can you go ahead and share your slides? Let's see if that works. Cross your fingers. Looks great.
And can everybody hear me?
Yes.
Okay, so I'm really happy that I went after Hanyu and Jerry because the project that I'm talking about today is in the very early stages. So I'm going to take a lot of what the two of you talked about and, a lot of lessons learned. So the project that I'm talking about today is a project that my colleagues and I are working on that aims to measure response latency using text analysis of interview transcripts from the Consumer Expenditure Survey. So the team is in the very early stages of the project and we're getting the project off the ground. So in this presentation, I'm going to discuss how the project got started and steps we are taking to get our hands on the data. So this project today wouldn't be possible without the existence of a computer recorded interviewing, or Carrie, which Hanyu already talked about a little bit. So I'm going to just skim over this, but Carrie uses the laptops or phones to record interviewer-respondent interaction. So at the start of the interviewer asks the respondent to consent to the recording, and if the respondent consents, then the recording is initiated when the interviewer navigates to the screen. So the recording is at the question level, not the interview level. So the entire interview is not recorded. So Carrie was first implemented by the BLS in July of 2022 after staff identified some unexpected aggregate survey responses for certain items in the Consumer Expenditure Survey. So the CE collects data on some kind of complicated expenditures, like all the different components associated with purchasing a vehicle, property, rent, insurance, major appliances. And the respondent is asked to recall these expenditures over a period of 3 months. So a research team was created to investigate what was going on. And this team uses the Carrie recordings to evaluate interviewer behaviors, like whether they make a major change to the question stem. And then we also evaluate respondent behaviors, like if there are any signs of burden or confusion, and then the interplay of interviewer and respondent behaviors. So on this team, we use traditional behavior coding techniques that require the researcher to listen to individual Carrie cases and then manually code features of the interaction based on a priori research questions. And this process can be time consuming, but it also limits the types of questions that we can investigate. And one aspect of the interviewer respondent interactions that can't be easily captured by manual behavior coding is response latency, or the time it takes a respondent to process and answer a question. So research indicates that response latency can be considered a proxy for cognitive processing and question difficulty. So basically, if a question is difficult, it'll take a longer time to process, thus increasing response latency. And a substantial body of research suggests that there's a strong positive relationship between question difficulty and response error. So typically response latency is measured by coders like literally pressing a button at the offset of the question reading to start a timer and then pressing it again at the onset of a definitive answer by the respondent to stop the timer. But that's not totally realistic and it's prone to error. And while we were working on the Carrie team, we learned that transcripts could be generated from the Carrie audio files. So we wondered if there's a way to measure response latency using text analysis. So these transcripts are created using AWS's Amazon Transcribe, and they provide timestamps, potentially making measuring response latency possible. So we learned about the possibility of the transcripts, and we proposed extending the research being conducted on the original Carrie team to include evaluating interviewer-respondent interactions using data science techniques. So we have 4 goals for this project. First, we want to identify whether an interviewer makes a major change to the question wording. And because there's going to be overlap in the cases that we're requesting for this project and those that were previously evaluated by the Carrie research team, we'll be able to compare cases identified as having a major change by our model to those cases coded as having a major change by the Carrie research team without adding any additional time to our project. So we'll essentially be able to check our model against actual human coders. And second, we're interested in if question wording predicts respondent behaviors that may provide insight into data quality, like whether the respondent estimates an amount or if there are any requests for clarification. And third, we want to identify if a major change to the question predicts response latency. And then finally, we're also curious if response latency predicts respondent behaviors like amount estimation and requests for clarification. So we expect this project to be ongoing, and we expect to investigate, multiple items. But for now, we're targeting 2 survey items that were previously evaluated by the CARI research team. And the first item is weekly expenditures for groceries. So the text in red is the question stem, and then everything else is an exclusion or inclusion clause that the interviewer reads to provide the respondent with more detail on what to include and what not to include. Right now, we are interested in the question stem only, and we're especially interested in the word usually and whether omission of usually affects response latency. And then the second item that we're looking at is the business screener and its follow-up item, which is received if the respondent answers yes to the business screener. Selection of this item was based off of results from the CARI team that found that approximately 20% of respondents switched from yes in the business screener to no after hearing the follow-up item. And when we originally listened to these items, it was unclear why respondents were switching their answers from yes to no. We think that maybe the interviewer may have framed the business screener in such a way that led to respondent confusion, but we're not sure. So for this item, we're interested in whether a major change in the business screener may predict an answer switch. And we also think that response latency may play a role, such that a major change in the business screener may affect respondent confusion, which in turn could affect response latency, making major change and response latency dual predictors of an answer switch. So to recap really fast, we learned of the possibility that transcripts could be produced from the CARI audio files. So we drafted a series of research questions that use data science techniques to broadly evaluate whether interviewer behaviors influence respondent behaviors, specifically response latency. But in order to do this, we needed to confirm that we could, in fact, get the transcripts. So BLS doesn't produce the audio files that generate the transcripts. Our partners at Census do. So on the original CARI team, we access the audio recordings of the interviews through a Census-created app called CARI Interactive Data Access, or CIDA, and we access CIDA through Census's VPN. So our mission is to figure out how to get the transcripts from Census to the BLS so we can get the analyses. And we met with the CIDA team over at Census to discuss the feasibility of conducting this research. And we discussed the format of the transcripts, and we compared the level of detail possible in the transcripts with the level of detail needed to accurately measure response latency. And in that meeting, we learned that the transcribed interviews are stored in an Amazon S3 bucket in the cloud, and then the files or objects which contain CE data and all of the associated metadata are uploaded into that bucket. So we now know where the data are, we know how they're stored, but we still needed answers to two kind of big questions. So can the data be pooled or copied from the cloud to be analyzed on our local computers, or will we have to work on the Census VPN? And then second, how much is this all going to cost? So to jumpstart the process of getting the data, we drafted a scope of work to send to Census. And in this scope of work, we specified everything that we would want, including the dates of the interviews and the questions we're interested in. We also specified what we wanted in the transcripts themselves. So we requested labels for speakers. We requested diarization, or those terms that Jerry and Hanyu were talking about. And we want to be able to differentiate between speaker 1 and speaker 2. And then in the scope of work, we also requested that the transcript data be included, have as much detail as possible. So specifically a word for word breakdown with timestamps, and then the timestamps should be at the millisecond level if possible. So we now know that the data exists and that the transcripts generated by Amazon can be sufficiently detailed for our purposes. And we learned all of this in our meeting with our partners at Census. So once we learned that this research was actually feasible, we put together a team. And this project extended from the original CARI team, and it builds off CARI research questions. So 3 of the 4 members on the original CARI team are also working on this project, but there's also a really large data science component, and we needed help with it. So we put together a disciplinary team to fill in any knowledge gaps. And this team includes 2 survey methodologists, a CE subject matter expert who also serves as a project lead for the original CARI team, and a data scientist. So full disclosure, we've completed steps 1 and 2, but we haven't actually gotten started on the like actually working with the data. So we are like really taking advantage of this session title, Works in Progress. But we have the team in place and we're waiting on the data. And once we get the transcript data, we will merge the transcript data from Census with the BLS data, which includes consumer unit characteristics and respondent characteristics. And then after the data are merged, we'll start actually building the model. And there are a few requirements for the model. So first, it should measure the frequency of major changes to the question stem. And like any other behavior coding research project, what constitutes a major change needs to be clearly defined. So for the grocery store item, we know that omission of usually is a major change that we want to look at, but we haven't yet decided on what a major change looks like for the business screener item. But once that's figured out, then the model will compare the interviewer question reading in the transcripts to exact question wording using distance measures. And previous research has shown that distance measures are effective tools for evaluating interviewer-respondent interactions. So we also want the model to identify paralinguistic expressions or verbal disfluencies like ums or pauses. And we are also interested in signs of verbal hesitations that may not be paralinguistic expressions like let's see or I'm not sure. And then finally, we want the model to measure response latency by calculating the time elapsed from the offset of the interviewer question reading to the onset of the first definitive response, if possible. And we say if possible after definitive response because working with unstructured interview data can be difficult. So if you think about your own conversations, right? Do we always answer a question with a definitive answer? When we're interacting with people, we may infer what they mean based off of a series of statements. So in our social lives, we use heuristics to make a judgment about some sort of response or action. And that's the same with interviews. So in some of these interview cases, we may not get a definitive response or we may not get an audible one. And the interviewer may enter a final response based off of respondent explanation. So the interviewer is using their judgment when no definitive response is given by the respondent. So we have to think about how we actually capture this. Do we define response latency as the measure of duration until the interviewer recorded response, or do we define response latency as the end of the respondent explanation based off the assumption that the interviewer believed there was a definitive answer embedded in these responses? We're still working through all that. So the project status,
wrap up soon.
Okay. The project status is just getting started. So up until this point, we've done a lot of thinking, we've done a lot of planning, we've done a lot of reading. We're submitting the scope of work to Census, who will then estimate a cost of copying the data from their cloud for our use. But in the meantime, we still need to operationalize a few key constructs like the response latency in the context of interview data and what constitutes a major change in the business screener item. And these are some questions that we have for the audience, if there's some time for questions.
Thank you very much. Thank you for the presentation. We are very short on time, and actually, I'm going to ask the audience We got started a little late. There's no session after us. I'm going to take our session to be 5, 6, 7 minutes beyond our original presentation time so that all of our presenters get their full time. Yeah, so take a look at the questions that Victoria has put up for discussion there. And if you can go ahead, type things into the chat, we can talk those through sort of offline while we get our next presenter up. Kevin, do you want to get your slides ready? And while Kevin's getting ready, I'll just note, I think that this project could really benefit from the wisdom from Jerry and Hanyu, especially maybe, Amazon's diarization might not be as good as we hoped. All right, go ahead. Kevin, I don't see your video. Are you up? And there we are. Take it away.
All right. Thank you. Erica, you can hear me okay?
Yes.
Thanks. Thanks, Erica, for setting up the session. Really appreciate it. And it's interesting to hear kind of what the other presenters are doing, because there are definitely some common themes in the work that this research is doing in regards to the audio recordings, especially. What we're doing in this project is looking at the use of machine learning for contact center operations, and specifically for looking forward to the 2030 census. So my name is Kevin Zajac. I work in the Decennial Census Management Division at the U.S. Census Bureau, specifically overseeing the planning of the telephone assistance operation design for the 2030 census. I was involved in the phone operation for the last couple of decennial censuses. So I have a fair amount of experience in the realm of contact center operations, but admittedly, I'm still learning about machine learning capabilities. But this research project has really made me excited about how our contact center operational design for the 2030 census might look and the innovations that are being considered from a machine learning perspective. This research has been a team effort, and I'd like to acknowledge the project team of Census Bureau colleagues from the Center for Behavioral Science Methods, especially Beth Nichols, as well as Monica Puerto and Brian Sadaka from Central Federal Services for their technical knowledge. This presentation will touch on the following areas of our research. I'll introduce the project and get into some detail about the goal of this research, as well as some of the background, help you understand why we are doing this research. I'll review the research questions associated with the project. I'll talk through the methods and process used to analyze our data. I'll describe some of our challenges experienced during our research, and at the end, I'll present some questions for you to consider to solicit feedback in areas where more information from others would be helpful. So the goal of this research project is to suggest improvements for Census Bureau contact center operations and identify ways to enhance the overall call experience for callers and live agents by utilizing machine learning methods. During the 2020 census, a contact center operation was stood up to assist callers over the phone. The operation was called Census Questionnaire Assistance, or CQA for short. Agents assisted callers by providing answers to frequently asked questions and questions about items on the 2020 census questionnaire. There was also the ability for agents to collect response data from the callers. The 2020 CQA contact center operation was handled by a large contractor and utilized 11 physical brick and mortar contact centers across the United States. Support was provided in a total of 13 languages, which included English and 12 non-English languages. The design of the solution used both an interactive voice response system and over 7,000 live agents. The automated IVR component, which was presented to all callers on the front end of the English and Spanish language lines, was menu-driven and used keypad entry as well as directed text to retrieve answers to questions. When responding to caller questions, agents were required to read responses verbatim so that they were providing accurate and consistent answers. To ensure data quality and customer service standards were being met, a manual quality monitoring component was performed on a sample of calls by a dedicated quality staff. Millions of interactions between callers and agents were recorded during the 2020 census with caller consent. During operations, these recorded calls were used for the quality monitoring I just mentioned, but the recordings were also saved after operations. These recordings are ultimately the primary data source that we've used for this research project. This is a graph of historical inbound call volume for the 2020 CQA operation, and it includes calls that ended in the IVR system, as well as calls that were handled by live agents. During 2020, the CQA operational period ran from March 9th through October 15th. More than 50% of total inbound call volume was received within the first 4 weeks of our operations. This gives you an idea of the challenging call pattern that we deal with during a typical decennial census. These large call volumes early in our operational period were primarily driven by mailings sent to all households across the country. As I mentioned on the last slide, we hired over 7,000 live agents for the 2020 CQI operation, and these agents were short-term and didn't necessarily have contact center experience. The call volume happening early in operation drives a need by these agents to get up to speed with census content quickly so that they can be efficient with assisting callers. Although there's an extensive training program, these live agents are being thrown into the fire and getting hammered with back-to-back phone calls as soon as they start taking live calls. So one of the big things we're trying to do with this research is to identify ways to utilize machine learning to assist them with their required tasks. This research is work being done as a part of the 2030 census design selection phase and will result in recommendations to the approach and design of the contact center operation for the 2030 census. And we have three main questions that we're trying to answer with this research project. The first question, can machine learning be used to automate systems so that they are more efficient for the caller and for the agent? This includes trying to reduce call handle time and self-service more calls in the IVR so that we reduce from the live agent. We're looking to make the IVR more user-friendly using machine learning so that a keypad is not needed, and instead the caller can say their question in a natural way and receive a pre-recorded message, resulting in less calls needing to speak with a live agent. Improving self-service in the IVR is important since more calls going to live agents will increase staffing costs. And while a caller is speaking to a live agent, we want the system to be designed utilizing machine learning in a way such that the agent can retrieve an answer to the call more quickly and accurately than through a manual process. Our second question, can machine learning be used to automate processes which would reduce human error and create a more uniform application of the processes across agents? Examples of this include the automated coding of call types, alerting a supervisor to intervene in a call when something is going awry, and monitoring quality performance of calls. And then our last research question here is, can machine learning be used to identify improvements to the frequently asked questions and other content used by the operation? And examples of this included identifying gaps or redundancy in the FAQs, determining current FAQ effectiveness, and helping to identify content needing revision. While this research focuses on creating process efficiencies, automating tasks, and creating a better call experience, the hope is also that this research will lead to cost efficiencies to our contact center operation strategy during the 2030 census, as well as being applied within our internal contact center. As I mentioned early on in this presentation, the primary data source we used for the research is recorded audio interactions between callers and CSRs from the 2020 CQA operation. About 120,000 recorded calls in English, Spanish, and Chinese from the 2020 CQI operation were used for this research out of a total of approximately 4.7 million recorded calls. We chose to look at calls in English and Spanish because these two languages represent over 98% of the calls that were handled by agents during the 2020 census. We also wanted to look at the effectiveness of using machine learning for a non-English, non-Spanish language, so we chose Chinese Mandarin. Text transcripts were then produced from the recorded audio calls. This preliminary phase of evaluating transcription models was very important because the quality of the transcripts affects the research outcomes. We looked at several different open source transcription models, making sure they were approved for census use. And we compared the output from speech-to-text transcription models to manually transcribe text to evaluate the effectiveness of each of the models. We did this primarily by looking at word error rates. Once we had what we believed to be the highest quality text transcripts, we then developed models using various machine learning techniques to answer our research questions. We always had to have a truth deck developed manually to evaluate effectiveness. Some of the machine learning techniques that we used included transformer models, topic modeling, and fuzzy matching. We've been able to make a lot of progress on this research over the last 2 years of it, but it hasn't been without some hiccups along the way. Some of these challenges have included the staff knowledge with machine learning models and techniques. We largely relied on 1 to 2 team members knowledgeable with machine learning to perform the analysis. We had some resource issues due to manual transcription, manual coding to determine truth. For some of our research, there was a need to do some labeling of data, which required humans to listen to a lot of recorded audio calls. This process was, as you can imagine, super labor intensive. Quality of the transcripts for our non-English languages. The text transcription models produced error levels for Spanish and Mandarin, which resulted in low confidence of the results in comparison to English. So while we looked at those other languages, the results were we were less confident in the results. Over 300 FAQs were available for use by contact center agents to answer caller questions, but a lot of these FAQs were similar in nature. These similarities have affected the predictions of the machine learning models. And then, as we all know, transcription models are evolving quickly. New models are being developed and existing models are being updated. So there's been a need during our research to perform constant evaluation and reevaluation. All right, so based on this research, because this research is largely focused on contact center operations, we're especially looking to solicit feedback from others in the same contact center area. First question, are there any federal agencies that use similar machine learning techniques for their contact centers? We'd love to hear any experiences, both good and bad, with implementing machine learning into your contact center operations. Any experience on determining the return on investment when it comes to utilizing machine learning techniques? And if so, how is it measured? One of the things we're trying to do as we prepare for the 2030 census is to get a sense for the impact that implementing machine learning into our overall design is going to have on contact center costs, technology, and infrastructure. Regarding computing power and speed needed to utilize machine learning in real time, any insights when it comes to providing responses to caller questions via an automated IVR system? And have you experienced any issues with the response time? One of our concerns with utilizing machine learning in a self-response way is by the IVR system, making sure that the caller gets the right information and also gets it quickly. So any experience with determining required levels of computing power might be beneficial to hear about. And then our last question that we're soliciting feedback on is to code whether FAQs need to be rewritten or new FAQs are needed. It would be great to have a labeled data set that coded whether the current FAQ answered the caller's questions. At the core of our contact center operations, the database of FAQs used by our live agents to answer caller questions are essential to providing good customer service. However, we don't always have a good measure of whether the information is giving the caller the information that they actually need. Does anyone add a question at the end, such as, did this answer your question? We didn't have a customer satisfaction question built into the 2020 contact center operation, but it's something we're considering as we move towards 2030. And then, I guess more interestingly, does anyone have experience with using emotion recognition to measure satisfaction? When we first began this research, we tried to use audio to measure some emotion, but ultimately found that the words were more effective in determining satisfaction or dissatisfaction. And that's where I'm going to end today.
Thanks. I'm going to go ahead and of course, invite all of our audience to put their questions in the chat, but I'm going to put Hanyu on the spot first, because I'm just thinking about that last bullet point you had, Kevin, about the motion recognition to measure satisfaction. And that reminded me of a question that I didn't get a chance to ask Hanyu about, because Hanyu, in your presentation, you made a quick mention of identifying confusion using, you had all this vocabulary that I hadn't, like shimmer and glimmer or other acoustic features, I think it was, from the recording. And I wonder if you've got anything that might help Kevin here.
So we're currently working on that right now. So what we have is we have human coded results. We ask them like different bunch of questions. That question about like how to what extent do you feel the respondent had a like comprehension issues or difficulty answering the questions, and then we're trying to use that as outcome measure and fit some models with acoustic features. But it's ongoing, so I don't have any results to present today. But that's currently we're working on that right now. But one thing I want to add about, as what Kevin have on this here, I felt emotion. The problem with the survey interview is respondents sometimes not right. Confusion will be one type of emotion, but it occurs, depends on the context, depends on the question being asked. I mean, other emotion like extremely happy, like sad, anger, that probably doesn't appear very frequently in survey interview because it's different from a day-to-day conversation.
Yeah, and it kind of like, you know, depended on the different types of phone calls we were looking at, because, you know, we did have the data based on like how the agents disposition calls, you know, and so some of them were like they could be threatening, they could be unhappy, you know, things along those lines. And so we had some of that information, and we definitely, for certain types of calls, you know, the emotion was valuable, but you could also determine sort of how satisfied or dissatisfied someone was based on the words that were being used. So, but I think to your point, you know, when they're actually going through a data collection of the actual census interview, it's probably pretty kind of monotone. There isn't sort of highs and lows associated with it. So.
Then I was wondering about, again, that sort of question number 4 that you got. When I think of FAQs, I think of them as, you know, it's a document that you can browse. Whereas what you've got is this, somebody gets to generate their own question. What do you, I mean, is it on the table to scrap this FAQ entirely and have, I don't know, some sort of text, you know, that some smart, you know, like ChatGPT can like read the text and figure out the answer, rather than this sort of constriction of FAQs?
Yeah, I mean, it's something we're talking about. I mean, this is kind of where this research is potentially leading to for 2030 for us. But we also want to make sure that whatever we're producing and whatever is being output, you know, we want to make sure that it's being conveyed consistently. We want to make sure that like they're getting kind of the full, I don't know, answer to the question. They're not just getting bits and pieces. So, you know, typically in the past when we've done this operation, we have sort of blurbs that are required by the agent to speak back to the caller, you know, and so we want to be careful that, you know, we're looking into what you're talking about, but we also want to be careful because we want to make sure that contextually, like, they're getting accurate information and kind of the whole scope of the information that they're going to need to potentially answer the question.
That sounds right. That tracks, because it's like the Census Bureau has the interviewers read scripted questions.
Yeah.
It would make sense that the call center would have to have scripted answers.
Yeah.
And again, I know we're over time, but if there's anybody in the audience who wants to ask a question of any of the speakers, now is the time. You can raise your hand or you can pop it into the chat and we can read it out loud for you. But otherwise, I want to thank all of our presenters for opening themselves out and putting out this ongoing research. It's not polished, but we got really interesting insights into what's going on. So please email the presenters. I'm sure that's okay, right? To email the presenters if you've got ideas or questions, or you want to get a copy of their slides. Please do that and keep the conversation going. Thanks very much, everybody. I think we'll call it. That's the end of our session. Thanks very much. See you at 1 o'clock for our next session.
Welcome and thank you for standing by. At this time, all attendees are in a listen-only mode until the question and answer period. This webinar is being recorded and may be posted publicly. If you have any objections, you may disconnect at this time. Now I'd like to turn the webinar over to David O. David, you may begin.
Thanks, Lisa. Hello, everyone. I hope you've been enjoying the sessions at the FedCASIC so far. My name is David O, and I'm a supervisory data scientist at the Bureau of Labor Statistics, and I will be moderating the session, which is titled Data Science Applications, Large Language Models. So this session is scheduled for 90 minutes. So we will be giving each presenters about 15 minutes to share their work. Then we'll reserve the remaining 15 minutes at the end for Q&A. So as presenters present, please submit your questions via chat. All right, so with that, I will now introduce our first presenter. So we have here Dr. Michael Link. He is President and Chief Research Officer of Ipsos Public Affairs in the US, which provides advanced data collection, analytics, and insights for solving clients' difficult information needs. This includes, Ipsos Knowledge Panel, the longest running probability panel in the US, Dr. Link is also a past president of the American Association for Public Opinion Research. His research focuses on the use of generative AI in the survey research and data collection. All right, Michael, when you're ready.
Thank you, David. I really appreciate it. Thank you all for hanging in there for the last half of the FedCASIC presentations. So question for you all. How many of you are using generative AI daily in your regular work? The same way that you might use Word, Excel, PowerPoint, R, SAS, whatever it is that you're using. Because that's where things should be right now in terms of at least the workplace. That this is an incredible technology and it really is an assistant per se. It doesn't replace us, but is an assistant. The big question though, obviously for us is, what implications does generative AI have for survey research data collection? And that's a bit different question than how we're using it in our daily lives to do some of the office type of work. So what I'm going to do is just focus a really basic kind of test today about using LLMs and different varieties, different types of them, and doing something very basic that we all do, which is try to code open-ended questions and kind of see where we go and see where this could take us. So just a bit of background. One of the things we're looking for here, what are the strengths, weaknesses of using large language models, things like ChatGPT, Google Gemini, Falcon, there's a whole host of them out there. A new one seems to come out every single day. But what are these? You know, for those of you that aren't terribly familiar, we don't need to get into the technical details. I've got some colleagues here on the panel that could do that. But essentially, large language models are models, and we're used to using mathematical models. But these are a very different type, far more sophisticated, and they're to try to replicate essentially the thinking of the human brain. The big difference here is that rather than simply having a model and have it be deterministic, here, they're trying to create models that can learn from the vast majority of information that's out there. So for us, the question becomes, as survey researchers, how can we take advantage of this great technology? And one of the key areas, because large language models really came out and deal with text, text is a great place for us to start. And one of the areas that all of us have issues with is open-ended questions and that ability to code them quickly, fast, those kind of things for different kinds of themes, categories, do sentiment analysis and that type of thing. So what we want to do is kind of look at here very basically, how might LLMs help us with that particular task? And where might there be some pitfalls? So basically what we did here was a very simple test where we have this panelist first approach that Nick Bertoni, my colleague, has initiated with our knowledge panel. And effectively what we do is we just ping our panelists every now and then with, hey, are you satisfied with being part of knowledge panel? Yes or no? And if not, or why or why not, in open-ended questions. So that yields us a set of data that we can use. Without going too much into the details, here we essentially took responses from about 5,000 folks that we got responses back from. Obviously, because folks are in there, a lot of affirmative, a lot of, very few negative, but that wasn't the point. The point was simply to have some open-ended fodder for us to be able to work with. We internally at Ipsos then have something, and you'll love this brand, Ipsos Facto. It actually is a very cool platform where we have access then to all of the latest models, about 7 or 8 different models that are out there, and then we can pick and choose internally which one we want to use, and it's firewalled. We've got some agreements in place with these companies, those types of things. But what I wanted to do is to be able to take these open-ended questions and start playing with the different models and see what happens when we run different types of iterations. So the first test was very simple. Using ChatGPT, a version of ChatGPT, using the 4.0 version, the question I had was, what happens if I were to take these open-ended questions, ask it to essentially come up with the themes. So essentially go through, and it's not going to code each one, but it's going to give me the list of themes. And I ask it to give me the frequency count on those. What happens if I run the same model, but I do it at different days and different times? One would think in the past, we love if we're going to run the same model each time, we're going to get the same results, right? So that was essentially what we did here. And one thing I do want to point out when you're using these types of tools now, and this has become new lingo in our area, is the prompt. So that prompt at the bottom is, what is it that you type in, the commands that you give? And I could tell you that providing your prompt is now going to become the new provide your questionnaire or provide your weighting code, because just like a questionnaire, if you change the question wording, you're going to get different responses. If you change the prompt, you're likely going to get different responses. So here what I did, same prompt, same version of ChatGPT, but I ran it across 3 different days. And what did we get? So essentially, you can see here it coded things and gave essentially I asked it for the top 10, and to go through and kind of code this in terms of the percentages. And you can see that, we did this over the course of 3 different days. And at the top, things seem to work out pretty well. We've got rewards and compensation. Each label was slightly different. Enjoyment and surveys was next. Then things start to break down a little bit. As you start to get to the smaller level of codes where there are fewer, you can really start to see here that the codes become different, the percentages become different. And so it's picking up on different cues each time. So big gist here was, even though I used the same model, I ran it over different times, I did get different results. The second question then was, okay, well, what if we were to vary the models? So those of you that know, you've got ChatGPT 3.5 that came out, and just like other software, you get these iterations. So you've got 4.0, 4.3.2, all these kind of things. The difference is obviously that they're improving these models each time. So the size, the parameters, the training data, the algorithms, performance, scalability, each time you move to a different generation, a different version, it's different, right? And in theory, it should be improved. So the question here was, same exact data, put it through. We ran it through essentially about the same time, so we try to control for time. But we used in sequence these 3 different models. And what did we get? Here you can see, while at the top we had satisfaction, rewards, compensation, basically the same thing. So rewards and that type of thing was number 1. Big difference in the percentage. The 3.5 said about 26% did that, whereas closer to 40% with the other 2 models. Then you can see, again, some of the same themes: enjoyment, desire for surveys. But as you start to work your way down again, these things really change. The percentages change, the rank order of these, and even basically the coded theme changes. So again, what we did here, same data, same time period, different models. So what are the implications here? So the implications are that it does a great job, very, very super fast, at being able to theme identify. Less than 60 seconds, boom, you've got this stuff out there. But it does, and the themes make sense. So there's construct validity. So when you look at the themes it came up with, and I looked at the real data, these are, if I were to do coding, these are probably what the code book would look like. But you do see, though, you get different labels and you get different percentages. And basically what the gist is here is that we're having a lack of consistency. So as we're using these models, varying over time, you had a little less inconsistency, but it was still there. When you go across models, you're going to get really different results. The other thing, and this was kind of interesting, this is maybe a researcher error, researcher finding, which is I didn't tell it to only give 1 code, which is why, if you remember back in those slides, they summed up to more than 100%. So with some of these, it went through, because there were like 2 different concepts, it gave it more than 1. So why the variation? Well, again, while we know at a high level what's happening, each of these is a proprietary thing, and it's something of a black box. And scarily enough, we have heard that some of the programming folks say that once these kind of neural networks and things start going, they're not entirely exactly sure how things are being pulled out. They know how it's coded, those kind of things, but it is something of a black box. Big thing for us is to remember that LLMs are probabilistic, not rule-based, which means unlike models that we run, where we fix the parameters, and if we run the same data through, you're going to get the same result or you better. these do have a degree of randomness in there, and that's intentional to allow things to evolve over time. The training data is different, the architecture design is different, the way it interprets context can be very different, and a host of other things. And again, models are evolving over time. So for us, these LLMs are made for a wide array of things. They're not necessarily directly made for survey researchers, or any researcher necessarily be doing consistent results over time. So I think that's something we're going to have to really deal with. I like to call this a perpetual dynamic algorithm issue, which is that the interest here, these are companies that are producing a product where increasing, the speed, the ability, the capability is part of what they need to do. We need to recognize that then, that these tools are going to evolve and change over time as we use them. That may change what it is that we're getting. Now, there is down at the bottom, there are ways to go through and be more sophisticated with some of the parameters. There's a temperature, there's other things you can do to try to reduce the variability, but basically you're still going to get the variability. So let me move to one last thing here, a third thing. This is somewhat different then. So one of the things that we developed, I said before, those last two tests where I simply ran all the results in there and had it code them. But what we really like to do is apply codes to individual cases, right? So at Ipsos, we've developed a tool that's called TACTIC, Text Analytic Comprehensive Toolkit. Basically, it's an interface that allows us to go in, upload our data. It will go to the models, and effectively what it does is it goes through and creates a code book first. You can kind of look at the code book, make the changes, and then ultimately, when you're comfortable with the code book, it can apply those labels at the respondent level. So I wanted to look at this and say, okay, what happens when we upload 270 respondents? This particular program uses the same model, GPT 3.5 Turbo. But again, you're going to be running these over time, so sometimes you may expect to get some differences. And again, conducted these two runs about 15 minutes apart. So what did I get here? So this now is the percentage, and these are coded down at the respondent level with one code per respondent. So we got almost 97% in each case. We were able to identify. The other 3%, there was either nothing there, or it couldn't apply a label. But what you can see is you start to get basically kind of the same results: survey rewards, frequency, compensation, interest on the first run. Second one, compensation, length, frequency, surveys. They're a bit, they're somewhat similar, but again, they are different. And the question then becomes, how comfortable would you be? Which findings would you actually use and report out? So just to kind of wrap things up here, big takeaway for me, again, LLMs are in the really early stages of being used for survey research and any other kind of data collection. There's tons of promise, but just like any new tool that we have, we really need to understand what's happening behind it. Not so much behind the scenes, but what are the strengths and the limitations in terms of what we're using it for? And there is a goodness of fit. Sometimes maybe a quick run and giving you those responses is better than having the replicability, exact replicability over time. So that's an issue that we just need to look at. The biggest thing I think, though, too, is that this becomes a tool for us, but it does not remove our need for being experts in what it is that we do, because LLMs work best when it is a human-computer interaction. It is a back and forth kind of thing. It's not the kind of thing where you're going to take a piece of work and give it to the computer. It's where you're going to go back and forth and use it to help hone what it is that we do. So I'm really interested in this particular area. I think I'm really interested to see what my colleagues have on the rest of the panel and just where this goes, because it's going to be an amazing world. Thank you much. We'll take questions at the end.
Thank you, Michael. All right. At this time, we'll have Francis Smart giving presentation. So Francis, as you're pulling up your presentation, let me introduce you and your co-presenter. So first, we have Francis Smart. He is a data scientist employed by Senso Consulting Group to support the General Services Administration. Francis has over 10 years of professional experience as a data scientist and is very close to completing his PhD at Michigan State University, studying novel applications of large language models. We also have Isa Bab, who is a business owner of the Sales Reporting Portal, also known as SRP, at the General Services Administration. SRP is used by contractors to report over $40 billion in annual sales and remit fees valued over $300 million per year. Isa provides SRP oversight for the ongoing enhancement projects as well as maintenance and operations of SRP. All right, at this time, I will turn it over to you guys.
All right, thank you, David. As David mentioned, the sales reporting portal is a system at GSA that receives enormous amounts of data. Contractors report sales data in that system. They have two options. Usually it's either they report sales data at the aggregate level or at the transactional level. Both have positive and negatives, and we'll get into that here in a second. But of course, at GSA, we prefer the transactional level data because we can do analysis on it. So with large data, we face different types of challenges. And here today, we're going to talk about the challenges in regards to classification of items that are being sold and that are being reported. Okay, at GSA, contractors that have a contract with GSA have to report their sales and they have to remit their fees for using the contract. So as this large data comes in, like I mentioned, different challenges, but today we're going to specifically talk about classification challenges and the use of zero-shot learning models in order to help us solve that problem. So on the next slide here, I'm going to just give a quick overview. I think we skip a slide. Yeah. So on the next slide here, I'm going to give a quick overview of the system that we use, the type of data that we collect, and then the challenge that we face. So here on the slide, I'll give a quick overview behind the transactional data reporting. So at GSA, at the onset of establishing a contract with a contractor, there's a negotiation that happens, and the contractor and GSA come to an agreement on the type of reporting that the contractor is going to do. So whatever they decide, that's what they're going to stick with for the life of the contract. So if they're reporting at an aggregate level, the contractor is obligated to follow something called commercial sales practices or price reduction clause. This is where the contractor consistently has to prove to the government that they're giving them the best pricing. So nowhere else is that contractor allowed to give a deeper discount than they give the government, okay? Contractors over the years have voiced their concern about that because it's quite burdensome. They get audited, and if they found that they did not meet that clause, then there's fees and penalties, etc. And so that is pretty burdensome. So the decision came about 2016, where we said, okay, we can forgo the CSP and the price reduction clause, the PRC. We can forget about that as long as the contractor submits transactional data. Okay, with transactional data comes a lot of benefits. We figured that the contractor already has this transactional data in their invoicing system, etc. So it's still a burden, but it's less burden than following the CSP and the PRC. Okay, so on the next slide here, now we go into why do we prefer TDR? TDR, or transactional data reporting, gives us data at the granular level. So now we can take that data and we can do analysis on it. We can do historical pricing analysis. We can do check out the seasonal patterns. We can answer questions in the government, questions like, when is the best time to buy furniture? You know, what is the quantity at which I can get the deepest bulk discount? Things of that nature. This type of analysis now empowers the government to be able to do negotiations with the contractors and to be better informed. Our contracting officers, by using transactional data, the analysis of the transactional data, I should say, then it'll give the contracting officer the ability to make informed procurement decisions. Okay. Let's go to the next slide. So now, as we're getting all this data, now we, theoretically speaking, we can do analysis, and we do analysis. Most of the data is usable data, and we can do the analysis that we described. In way of a background, also, I want to mention that whenever a contract is awarded, the contract itself spells out what the contractor is allowed to sell, okay? Whatever products or services, but those items are not listed individually in the contract. Instead, the contract references something called the special item number, or SIN. Okay, a SIN is a categorization of products or services, and then the contractor can sell anything that's under that SIN. Okay. Now, a GSA, there are three types of SINs. Some that are strictly for products, others that are strictly for services, but yet others are either both products and services. So here's the problem statement. Whenever a SIN, or this category of items that the contractor can sell, if it's for both products and services, it makes it challenging for us sometimes. If the description that the contractor is reporting is not clear enough, it makes it actually quite challenging, almost impossible, to determine on our side if the item that is being reported is either a product or a service. And if we don't know what the contractor is selling, then really all this data that's coming in, or the data that we cannot decipher, becomes useless, right? We cannot use it for analysis, and we cannot make ourselves smarter, whether, to determine what's fair and reasonable pricing, what's a good price compared to the commercial pricing. So that data now becomes unusable by us. So next slide here, we'll just talk a little bit about, what is our objective then? As I mentioned, most of the data is good and usable, but we want to design a classification model so it will help us identify the items, either a product or service, okay? And when we do that, now we have better quality data, and it'll enable us to better analyze those products and services and determine fair and reasonable pricing, as well as help our contract officers become more informed and to make better informed decisions in regarding to procurement. So with that, thank you for listening to me when I do the introduction. I'll turn it over to Francis. Go ahead, Francis.
Thank you all. I'm very happy to be at this FedCASIC. I'm going to talk about the challenge of PDR. So when we're talking about machine learning classification, one of the big challenges is that the data tends to be very large and very heterogeneous. And the language itself, oftentimes the description, is not standard English. So just let's think about this. So we have 9 million rows since 2022 plus. It represents about $35 billion in reported transactions and 1 million unique descriptions since 2022. That's a remarkable number of unique descriptions. And then with regard to the SIN numbers, the special item number, there's 835 of those. And they allow us to classify it into different categories. So their top categories are going to be IT products with total value of 34%, and IT product professional services, which is 27.1%, where the industrial products has like hardware tools. There's quite a number of transactions like hammers, nails, et cetera, and that's about 41% of our transactions or rows. And then the office management also has about 30%. So the SINs give us some information, which is quite interesting, quite helpful to have this level of detail, but we'd like to get more detail, like what particular products are very high value, what particular services are very high value. And then there's also the risk that the contractor doesn't necessarily file the correct row. I don't know if someone's off of mute, but maybe they should turn their speaker on mute just because I'm picking up some background noise. There's also the risk that an individual contractor might not be filing their transaction under the right SIN. So with regard to what Esau brought up, that there's this, we have product services and some SINs which are matched as either product or services. And though they don't represent a huge amount of our data, about 21% to 25% of our transaction counts, that's a significant amount of data, which we basically have completely different validation procedures for products which are filed and for services which are filed. Products, we're checking unit of issue, price per unit, manufacturer name, manufacturer part number against the GSA Advantage catalog. We check if the price is competitive, if the price matches the catalog or is above the catalog. Services, we're a little more nascent than that, but the idea would be the price per hour is matched with the service labor in the contract. And then, but unfortunately, there's not that many codes that are available, if any. And so we really have to look at the description to get more information. But we're starting with a more basic question is, can we identify what's a product and what's a service? And then there's also the slight issue where some of the contractors, as I said before, they end up filing what is a service underneath the product and what is the product underneath the service. So we also want to detect non-ideal matches. So when we're looking at this, we already have these categories. In theory, we just like to use like traditional machine learning procedures. However, on experimentation, they did not perform very well. And this is, I think, the biggest issue is that many of the there's a few prominent contractors who end up reporting a lot of products under the service SIN just because they just group them in there, or vice versa. And it really throws off these predictive algorithms, especially when there's so much non-standard English in there. So at this point, we decided to experiment with zero-shot classifiers. Zero-shot classifiers they're trained. It doesn't rely. It's trained on large amounts of a large volume of data, a large volume of language data. It relies on semantic understanding to infer characteristics of unseen classes. I think we all kind of understand that. We're going to the session. Yeah, so it's important and useful because the categories don't have to be categories in which it was explicitly trained on. And I talk a little bit about this. So the particular one that we end up using is BART large MNLI, which is, it's just we tried various models. Of course, you just try whatever is available and you see what fits. Some of the large language models like GPT-4, GPT-3, Gemini, Claude, all these things, because the data is sensitive, we had to be able to run it in our local environment or on our AWS EMR server. So yeah, I will kind of skip over this since we're running low on time and the results are a little more interesting than just talking about the generals. So when we're thinking about these large amounts of data, I mean, we're talking, 9 million rows a day of transactions. I mean, not a day, a year of transactions. I mean, it adds up quite a bit, and almost no model, unless we're going to utilize some serious horsepower, is going to be able to classify all of those in an efficient way, just because it's too much data. It's too costly. But if we reduce it, and if we cut the data to only transactions, and if we sort by the transactions which particularly are high value or high count, then we're able to reduce the problem to a more tractable number. So for instance, if we just look at the top value transactions, grouping by description, we look at those which are less than 1,000 rows. I mean, in the top 1,000, that represents 53% of all the value of our data. If we look at the top 10,000, that represents 81%. And going up to 100,000, that represents 98% of our value. The counts, however, are a little more challenging because many of the values, I mean, they're more diverse and less lumpy. And in that case, we can see that the first 1,000 only represents 23% of the data. The first 10,000 only represents 51% of the data. We really need to go up to 100,000 just to get 80% of our data. So in our initial take, we're just looking at the top 10,000 in terms of value. So when we're thinking about how to set up the zero-shot classifier, it's pretty important to figure out what are the relevant classes, because when there's not a class which fits the product or the transaction, the algorithm doesn't know what to do with it. And you might throw in a category like other or something like that, which is something we tried as well. But this is the categories we ended up coming up with. And when we're thinking about services, professional service like labor hours and products, it's a little more ambiguous than you initially think it is, because what happens about what do you call a cellular service? Well, it sounds like a professional service, but it's really a product. What do you call a warranty? Well, a warranty is a guarantee of labor hours, right? To fix something or to replace a product. That's probably a product as well, since it's sold per unit, not hourly. But when you're asking a zero-shot classifier, you can't end up giving a long description of what the category is. You can't be like, and you just have to figure out the right words. And it's similar to programming like with LLMs, like Michael was talking about. It's very sensitive to the prompt. And then when we're talking about a product, another thing that might throw it off is like, what if you have a product that comes with the installation cost? So Yeah, I mean, it's a tricky bit when we're talking so many different transactions, so many different types of products or services. And then, so this is the a little bit of the prediction. So the SPs were about 2% of the data, products are about 28% predicted, professional human services 31%, software 23%. Let's see, I'm just checking the time. Okay, so how we actually evaluate the results? So we in this particular application, we only looked at those top 10,000, but for figuring out the results, what we did was we hand coded the top 500. So hand coding the top 500, we had 412 discernible categories. That means that the remaining, I think it's 88, were not discernible categories. That was, there wasn't sufficient information in the description in order for the human to assign them to one of the categories from the previous section. 170 of them were labor hours. And so when we're using the zero-shot classifier, it gives us a threshold weight at which, it gives us a weight of how strong it thinks a particular prediction is. And depending on the weight, basically it gives us, that maps into an accuracy. So the overall accuracy, we can see is the third column, about 0.4 was about 70% when we're talking about all the categories. But the category we only care, remember when we flip back over here, we really only have two categories, maybe with the other as well. We have product and labor hour. Those are the things we care about. And so even though we're not 100% sure, when it's, say, assigning something to a software versus a product, we don't really care as long as it assigns it to a non-labor hour. And so the overall accuracy is only 70%, but when we look at actual labor hour accuracy at 0.4 threshold, that's 83%. And then that actually maps really well because we're not having that much drop off. When we have a threshold of 0.4, we have 82.5. So we have half a percent that's being lost there, just about. If we bump up our threshold cutoff to 0.6, we're up to 90% accuracy. But now we've dropped to 49.5% overall identification. So of course the ideal strategy is to select as both thresholds with the higher threshold weight, giving us more confidence that we're actually successfully predicting labor hour category, and the lower weight giving us where we can say we're we have an 83% likelihood or something like that. That we've successfully predicted labor hour. And now I think I'm running out of time. So the next steps in this process would be to fine tune the model and probably scale up the number of hand-coded results, scale it up in terms of NLP, try to map out from not just 10,000 to really processing the bulk of the data. A nice target would be 8% of value, 8% of the counts. And then just to think about this, labor hour and services, it seems to work pretty well. But there's numerous other applications that the same technology could go if you have specific questions and you don't have those categories pre-assigned to a gold standard to train the model on, for instance, desktop computers, laptops, software suites, all these things which they sound like they should be easy to figure out, but because they're customizable software, they don't really have single part numbers that are as easy to map, and they also tend to be high value for the government. Thanks for our presentation. I appreciate it. Feel free to contact us if you have any questions.
Thank you, Francis, and thank you, Isa. All right. Next up, we have Wei Huang. As you're sharing your presentation, I will introduce you. So Wei Huang Wang is a principal data scientist at NORC. His federally sponsored survey projects include the National Survey of Early Care and Education and the Survey of Doctorate Recipients. He has also worked on other large-scale data collection and analysis projects for the federal agencies, such as the Synthetic Healthcare Database for Research and the Healthcare Cost and Utilization Project. Wei Huang, please take it away.
Thanks, David, for your introduction. Good afternoon, everyone. As David said, I'm Wei Huang Wang. Please call me Wei. I'm a principal data scientist at NORC, and I'm happy to be here today to talk about our work on using large language models for other specified coding. Before I begin, I'd like to tell you a little bit about the National Survey of Early Care and Education, or the NSECE. The work I'm presenting today is part of our work for the 2024 NSEC, and it uses data from the 2019 round of the survey. The NSEC is a nationally representative survey of the supply of and demand for early care and education, and the survey is sponsored by the Office of Planning, Research and Evaluation in the Administration for Children and Families. NOC conducted this survey in 2012 and 2019, and we're currently in the midst of collecting data for the 2024 NSEC. So here are the 3 acts of my presentation today. Act 1, I'll talk about what we did in our experiments and dive straight into our findings. To preview our results, they were not bad, they were not great either. So in the second act, I'll unpack the challenges we encountered by asking a very basic question. Why do respondents choose other when they answer a survey question? And in the third act, I'll share how we made lemonade out of lemons, and I'll conclude with some learnings from our experience. Okay, let's start. So for those who are not familiar with other specified coding or OS coding, here is an example which we're going to use as a running example throughout this talk. Here, childcare providers are asked to characterize the type of building in which their program is located. For example, a religious building, a public school, a private school, all the way down to a home apartment or other residential structure. Most respondents will choose from one of the named options, but some may choose other and then write in their response. So, for example, a respondent might write in ground floor commercial space of condo. And in OS coding, what we'll do is to recode it as option 9, home, apartment, or other residential structure. So dealing with these kinds of other verbatim responses is important to help researchers analyze the data, but it presents big challenges in terms of time, labor, and overall management of the process. We need to recruit and train coders as well as expert adjudicators to resolve any differences between coders. Over the past couple of years, we've seen major advances in the abilities of LLMs to process natural language. And as a practicing data scientist, the promise of LLMs is that you can now do natural language processing without actually being an NLP specialist, for better or for worse. You really just have to know how to use an API. So the main thing is that it's cheap and easy to experiment with these models. So given that the barriers to entry are now lower, we thought it was worth exploring whether LLMs could help to streamline the coding of other responses, ultimately reducing cost and effort. For instance, we could replace one human coder with an AI while keeping 2 humans in the loop. In running this experiment, we also aim to use open source LLMs deployed on everyday hardware. So commercial LLMs like OpenAI's GPT or Anthropic's Cloud may be state-of-the-art, but confidentiality policies may prevent the use of such services. Alternatively, there are open source models that are competitive with commercial LLMs, but they may require specialized hardware to run, and not all organizations have access to such hardware. In using open source LLMs deployable on consumer-grade hardware, our goal was to develop a solution that, if proven successful, could be widely applicable to a diverse range of projects across various computing setups. Now let's dive into the specifics of our experiment. Here is a questionnaire item on building type that I showed you previously. For our baseline prompt, which we call version 1, we first outline the task by saying that you are a helpful survey assistant. Your task is to categorize open-ended text into one of the following categories. We then list the response options and provide specific instructions to the model on the text that it should generate, and then we provide the open text to be coded. So our expectation is that the model gives us the number of the category that the open text should be coded into. We also tried 2 other versions of this prompt. Version 2 is a bit more detailed, adding the phrase, "My program is located in a," to each of the response options and also to the instruction. And then the third option is similar to the third version, is similar to version 2, but we move the open-ended text that needs to be coded from the end of the prompt to the beginning of the prompt. In this experiment, we randomly selected 100 verbatim responses that we collected during the 2019 NSECE. These responses were previously OS coded by human coders, and we'll take these codes as the ground truth. We then fed these responses into 3 different open source large language models, namely Llama, Orca, and Mistral. We ran these models using the llama.cpp software, which provides some optimizations that allow LLMs to be run on consumer-grade hardware. We fully combined the prompts and models to create 9 prompt model pairs, and then we ran each pair 3 times. So we did 27 trials in total. All right, so here are the results we got, which were mixed to say the least. This bar chart compares the average proportion of LLM backcodes that match human codes across the 3 trials for each of the 3 different model prompt combinations. The short vertical lines show the range of the correct proportion across the 3 trials for each combination, while the dots represent the average Cohen's kappa coefficient across trials. So what we see here is that the models agreed with human codes anywhere from 10 to 50% of the time, which isn't great. The models achieve Cohen's kappa values between 0.2 and 0.4, and substantively this means weak to moderate agreement with the human codes. So we could look at these kappa values and see the glass as either half full or half empty. The half full view is that the huge variation in performance clearly shows that with better prompting and with more advanced models, we can definitely improve the results. Right, so I don't think that the results we obtain are the best we can achieve, and I'm confident that we can do better with more tweaking of our prompts. The half-empty view is to conjecture that there is a ceiling on performance, especially because in practice, we don't have infinite time and money to keep fine-tuning the prompts. And whatever this practical ceiling on performance is, it doesn't meet our quality standards. So where does that leave us? Before I answer that question, let's pause here to put on our survey methodologist hats and actually think about why respondents select the other option. So there could be several explanations. First, respondents may be unsure about the words that we use in the question. For example, a daycare center that's located in a commercial space on the ground floor of a residential building may be unsure about whether this space counts as a structure, right? Whether this is a commercial structure, and rather than guessing, they left the decision to us. Second, their response may not align with any of the provided options. For example, a respondent may feel uncomfortable trying to categorize a daycare center located on a military base into any of these listed categories. Third, their response may fit into multiple categories. For example, a Catholic school might be categorized as either a religious building or a private school. So when we think about all these different explanations, it becomes clear that OS coding is actually a pretty challenging task for large language models, right? Because we're asking these models to tackle a task that a non-expert human finds difficult. And furthermore, these models don't have the specific substantive and policy context related to our study, which could result in categorizations that are technically correct but substantively wrong. As an example, if a respondent mentions that their program is located in a Catholic school, is this a religious building or a private school? And it's clear that both options are literally correct, but you might imagine a context in which we would prefer to code it as a religious building rather than a private school if researchers or policymakers have an interest in daycare centers that are located in faith-based settings. We can hypothesize that in many cases, this is precisely why respondents choose the other specified option. They're telling us that they don't have enough context to select the best answer. So now, Act 3, in which we try to make lemonade from lemons. And I think the thought here is, what if our ultimate goal isn't in fact for models to have a high degree of agreement with human coders? So maybe the biggest opportunity here isn't in delegating OS coding to language models, at least not yet given their present limitations. right? Maybe what we should do is to leverage the model's perceived limitations and the so-called mistakes they make to enhance human coding abilities and processes. So the basic approach here is that we look for the most common differences between human and LLM codes, and then we use it to develop guidance for human coders. If you accept the premise that LLMs have, in some sense, textbook knowledge about the world at the level of an entry-level analyst, then the idea is that the mistakes that the models make are likely to be the ones that our survey assistants might also make. And so we could use these mistakes that were made by the models to develop guidance for human coders before they've even coded a single case. Another way to think about this approach is that rather than spending time trying to improve the results from our models, we use this time to use the models to improve the quality of our human coding. Let me give you a couple of examples to fix ideas. And I should know that these are not necessarily the exact verbatims that appeared in our data. I've made small changes to protect the confidentiality of our respondents. So going back to this Catholic school example, right? The LLM quite reasonably categorized this as a private school. But as I said, you might imagine a context in which we would rather classify this as a religious building. Another example, for a response like leased facility from housing authority, the model coded it as an independent structure where we are the sole occupant. And again, this categorization might be literally correct, but again, we may prefer a code that more specifically characterizes the residential setting of the program. A human coder may not be aware of these specific preferences without proper training. So what we might do is to look at the cases where the models most commonly differ from the correct human coded answers. And here we got an LLM to generate the justification for why we might prefer the human coded answers to the model generated ones. And then, we'll give this feedback to the human coders. Of course, this feedback could be written by a human entirely or by a human editing the work of a model. It doesn't have to be done by an LLM. But either way, by systematically analyzing where language models deviate from human-coded ground truth, we can develop resources and identify potential blind spots to strengthen areas in which human coders may make unintentional assumptions or lack specific background context. So to conclude, if there's one takeaway from this talk, it's the importance of exploring the spectrum of human and AI collaboration when integrating AI into our workflows. This spectrum encompasses, on one side, purely human tasks, and on the other side, fully automated AI processes. But I believe the most interesting applications lie in the middle. And as Michael said in his earlier presentation, there's a lot of, I think that the best workflows result when there's back and forth between humans and the AI, right? So the collaborative mode involves humans and AI working together on different facets of a task, leveraging the strengths of both. The delegated mode entails assigning tasks to the AI while humans verify the results. And I think it's important that we explore and experiment with both of these categories when considering how AI and LLMs can optimize our survey workflows. As models improve and as we get better at prompting, the opportunities to automate or delegate manual survey coding tasks will grow. Still, fundamentally, OS coding is a challenging task for models, almost by construction, right? It's no ordinary classification task because you're asking a machine to do something that a human couldn't do. But this doesn't mean we give up on LLMs. I think it's just the opposite. I think what we figured out here was a way to rethink our coding pipelines in a way that takes full advantage of the combined strengths of human analysts and modern language AI systems working in concert. And this is particularly exciting to me because it offers us a way to level up less experienced or non-expert staff by providing them with guidance and guardrails. That's all I have. Thank you, and I look forward to your questions.
Thank you, Wei-Wang. All right, so at this time, we'll have Irina share your presentation. So Irina Bilaeva is a Chief Application Architect with the Research and Methodology Methodology Directorate Center Enterprise Dissemination at U.S. Census Bureau. She is leading AI projects aimed at improving discoverability of census surveys via data science and artificial intelligence to empower evidence-based decision-making. Dr. Bilaeva holds a PhD in computer science from the University of Maryland, Baltimore County. She is passionate about application of large language models for data analysis and is looking forward to sharing her insights at this conference. All right.
Thank you for introduction, David. And let me get started. So good afternoon, everyone, and thank you for joining my presentation today. So my name is Dr. Arina Bilaeva, and I'm excited to present on enhancing data analysis of federal surveys with large language models. So before we begin, let me give you a roadmap of my today presentation. And let's take a look at the key areas I will be covering. First, I will discuss the current limitation in analyzing federal survey data. Next, I will introduce a generative AI approach via large language model for data analysis. And finally, I'll explain how these LLMs can be applied to data analysis tasks such as semantic search, summarization, captioning, and information extraction. So let's delve deeper what the challenges we're facing in federal survey data analysis. So federal surveys, it is a vital source of information about everything, and they provide valuable insights about economic trends, public health, education, social demographics, and so on and so forth. But there are challenges in both in finding and understanding the data, and let's explore these areas in more details. For example, the first challenge is survey's discoverability. So to identify relevant surveys and datasets is really a daunting task. And for example, consider this. The data census.gov platform alone it hosts overall 6,000 datasets. And row-wise, these datasets like about trillion and trillion rows. So finding the specific data that we need within this ocean of information can be very time-consuming and challenging. The next problem is, besides in the discoverability domain, it is also a problem of insufficient metadata or lacking some context of details, so can further impede our ability to find relevant information. So besides discoverability, it also a challenge to understand the data have been presenting. Even after finding the relevant survey data, there is a problem to accurately interpret. It is very complex task for a regular user. So this requires a deep comprehension a multiple factors, including context of the survey, the methodology it was used for data collection, and specific terminology maybe not known to the public in a question by themselves. So how are we going to solve it? The approach is to use generative artificial intelligence, specifically large language models. And these AI models, as we know, they represent the state-of-the-art approach to address both data discoverability and semantic understanding. And the approach is via metadata summarization and semantic search, we can tackle these challenges. For example, imagine we having a multiple AI assistants that help us to understand the world of federal survey data. And with next generation of technologies such as LLM, this vision can become a reality. So there are three key ways LLMs can support us in this journey. It's first of all, semantic captioning of the data sets, providing intelligent search overview, as well as fact-finding assistance. Using semantic search context, we can go beyond just keywords and have an understanding of the user intent when they're searching for survey data. For example, let's imagine somebody asking a question about a federal survey dataset and getting a clear, concise answer directly from the data itself. So LLMs, they can act as a fact-finding assistant and help us understand and extract specific information and insights from complex data sets. So let's put that theory in practice, and in this slide I showcase the general approach, how we can leverage large language model assistants to analyze data in federal surveys. So imagine a user interacting with the platform or data catalog that contain information about various census surveys. So the LLM assistant is equipped with understanding of the data and the user intent, and can answer questions and provide insight directly from the surveys. So having understanding like about general approach, we can have a team of LLM expert assistant that dedicated to help us navigate through the world of like federal surveys data, and obviously with LLMs that becoming a reality. So in this case, I highlight 3 key ways LLMs can empower us in data analysis. Like, for example, we can have metadata summarization assistant, semantic search assistant, and fact-finding assistant. So metadata summarization assistant, it takes on the challenge of understanding complex metadata. The metadata summarization assistant is powered by semantic annotation and can automatically generate summaries of the survey and dataset metadata in a clear, concise way, and basically in human readable language. So this would save a lot of time and help users to understand the key details of each survey. So another assistant is semantic search assistant. It uses the power of the semantic search to understand the true meaning of the user intent and not just keywords. So this capability allows users to discover relevant datasets based on the intent behind the user query. For example, this assistant can provide a semantic caption that summarizes the answer and giving the quick overview of the data. And finally, fact-finding assistant can act as a personal data analyst, helping understand the specific insights. For example, imagine we're asking a question about a survey and receiving clear, concise answer directly from the data. So this assistant would leverage LLM's ability to understand survey questions and provide like factual responses. So I explain technical architecture of these LLM assistants on the next few slides, as well as I provide examples. Specifically on this slide, I go deeper in architecture for the semantic annotation for the survey metadata. So we can see there is various components like embedding API, Hugging Face libraries, and response summarizer working together to process and understand the survey details. So let's zoom in how LLMs can help us reimagine survey metadata analysis for census surveys. So this slide is basically show that LLM can unlock the meaning of the hidden insights within survey metadata. On the left, we have survey metadata like title and columns, and the LLM presented by the large box library Hugging Face LLM like going to work. So it analyzes the data, and with the help of like other components like embedding API, prompt engineering, and generates a semantic caption, which essentially it is a condensed summary that captures the essence of the surveys. So let's see how LLM would turn this data into insights. And this slide illustrates the magic of LLM-enabled metadata semantic annotation. So on the left, we have a row of main metadata, which is title ID, short title, and about 100 metadata. So this data goes through LLM processing pipeline, and the right side shows the output enriched metadata. So LLM essentially analyzes the raw metadata and generates more meaningful description, which makes it easier to understand what is the survey about, and users they can make their choices. In other architecture, I'll talk about semantic search architecture for census survey discovery. Well, in this architecture, first the user enters their search query, and LLM through components like embedding API and Hugging Face models converts that into query with into numerical representation that captures the essence of the user query. Then a retrieval engine locates relevant datasets from a massive storage that's called a semantic index. And semantic similarity search is performed to identify datasets that align closely with the user intent. Additionally, the query context engine might analyze query and data and provide even like more relevant result based on the context. So finally, the response synthesizer translates data into user-friendly summary that answers the user search question. And now let's take a look how it works in practice. So this slide shows the steps involved in LLM enabled semantic search. The user starts by entering their search question, and then powerful AI model is going to work. So LLM analyzes the query to understand what the user are really looking for. It creates like multiple questions to arrive to the final answer, and retrieve the more relevant data sets. And finally, the user receives a response that summarizes the data in a user-friendly way. And this is how LLM can reimagine the data discovery in federal surveys. The last architecture I would discuss, it is like dataset fact-finding architecture to answer questions, specific numerical questions about datasets. So in this case, LLM goes again through embedding API and Hugging Face model and converts user again to the numerical representation. However, difference in this case, it is like box in the middle. Number 3, so query engine API, it translates the user question into structured language SQL statement that can be understood by the database system where survey data is stored. So basically, this SQL statement is executed against the large knowledge base indexed federal survey data. So finally, the response generator, it generates the takes the retrieved data and transforms it into clear, concise answer to answer to the user question. Specifically, let me show the example how it works. Well, so we have an input, a demographic data set, and factual question about it. And let's take a look at the question. So it asks, like, for example, what are the top 5 states with the highest population in the United States? So the LLM then goes through their pipeline and retrieves and analyzes the relevant data from the demographic data set and answers the question. And here the question section, we can see that system provided the clear answer, what is the top state by population in the United States. Okay, now let me cover how performance of these 3 assistants were analyzed. So we have used 2 major evaluation categories. First categories, it is task adapt machine learning metrics and responsible AI metrics. For example, for tasks like semantic annotation, we measure how well LLM generated annotation match those created by humans, so-called annotation quality, and how they similar based on the scoring system. We also use standard measures like F1 precision and recall to assess the overall accuracy of LLM annotations. And similarly, for semantic search, we use query context relevancy recall at K, which measure how well the retrieved dataset align with the user intent and the effectiveness of overall search process. And finally, fact-finding tasks, they evaluated based on the answer accuracy, ensuring that LLM provide correct answers to user questions. And finally, responsible AI metrics, they encompass fairness, bias, and safety checks to make sure the LLM system is operating without biases and mitigating any potential risks. So I have discussed the metrics and give you I want to give you some numbers. So we can see that LLM assistant perform pretty well on metadata semantic annotation tasks. We have 92% precision recall, very high, and F1 metrics. As well does very well on semantic search. Here we can see that recall is pretty high, 92% that I would expect from LLM. On the fact-finding task, we have a little bit lower accuracy, but we have the work to do here, as well as on responsible AI task. Important metrics like coherence of the response to the user question, fairness, and so we can see here is almost zero, near zero hallucinations and toxicity of the response. Now, let's talk about the challenges in the with this LLM-powered data analysis of federal surveys. First of all, as we know, they are powerful tools, but no technology is perfect. The first challenge is it is tabular content modeling for discoverability. Essentially, how well LLM can understand and organize the structured data in survey tables to make it easier to find user what they need. So another challenge, how we can tune these models on out-of-domain tasks and how LLM can adapt to the different data set than they were trained on. Another challenge is also limited structure understanding of the data. How well LLM would grasp the structure and relationship within survey data, and there is different approaches how we can model it using just an index, or we can use graph databases. And finally, the risk mitigation here is crucial. So we need to make sure LLMs can be can be used safely by public, specifically open platform like datacensus.com. So in summary, let me summarize the way how LLM they can reimagine data analysis of federal surveys. So basically, LLM can unlock very valuable insights hidden within survey data by their ability to understand and process natural language. And there are two key functionalities. It is survey discovery via semantic search and automated fact finding. So to summarize the key takeaways from this talk, LLM they provide a very powerful ability to perform evidence-based decision making for humans. So, for example, by providing data-driven insights from the surveys, LLMs they can inform policymakers and strategic analysts and specialists make policy decision and strategic choices in a much better way. Thank you.
Thank you, Irina. All right. Looks like we're cutting pretty close to time, but we do have one last presenter, Rob. We have Rob Chu, who is a senior research data scientist at RTI International within the Center for Data Science and AI. Rob uses his expertise in machine learning, data visualization, software development, and computational social science to help subject matter experts solve their complex data problems. All right, Rob, if you're able to share your slides, and I apologize, but if it's possible, if you can give your presentation within about 15 minutes, and then if we have any questions at the end, we'll try to tackle them as we have time. Thank you, Rob.
Gotcha. Let's see if it'll let us. Okay. David, would you mind sharing the slides? Any chance?
Will do. Hold on a second.
I'll try to leave us time for questions, but no guarantees here.
Hold on a sec, sorry. Okay. All right.
All right, thanks everyone. The name of my presentation today is Using Large Language Models to Support Survey Coding. And this is joint work between a couple collaborators, myself and a couple collaborators, RTI, John Bolenbacher, Michael Wenger, Jess Spear, and Denise Kim. Next slide, please. So as a quick plug before we get started, this presentation is mostly a summary of some work that we did about a year ago and is now available for a preprint up here. If you're interested in more details on our approach or findings, please go check it out for more. Please go check it out. And that being said, since a lot of this work was done a while ago and large language models are such a fast-moving field, I did want to put in a little bit of extra here in the slides if we do have time. Next slide, please. Okay, so pretty much all these presentations have been about survey coding, so I probably don't need to motivate it why we do it, or the fact that large language models and machine learning in general can be very helpful because it can be very manually taxing to do coding because it's slow, expensive, and potentially error prone. What I did want to mention here in this nice pastel diagram to the right is that survey coding is part of a larger collection of methods called qualitative coding, which is often divided into two groups based on how the categories are you're coding for are created. So right here on the left, in deductive coding, you develop codes, categories of interest a priori before you see any data. And now deductive survey coding is often where you see opportunities for things like auto-coding and supervised machine learning, like the great work our moderator David and his team at BLS are doing with the SOI autocoders. In contrast, on the right here, in inductive coding, we develop categories of interest a posteriori, so after seeing your data. Inductive survey coding is common when you don't know what the categories should apply beforehand, like in another specified field like Wei Hong talked about in his presentation. And if you can't tell by this pretty blue little star here on the diagram on the right, we're going to be talking specifically about large language models and deductive coding. Next slide, please. Okay, very quickly, to get us on the same page, I wanted to go through this diagram, outlining the steps in a typical deductive coding exercise. This diagram loosely follows a process outlined in Nurendorf from this nice book, Content Analysis Guidebook, which uses ideas from survey research actually to inform how to conduct an ideal survey or ideal content analysis. So in deductive coding, we go all the way to 1 in the upper left-hand corner. We first develop a categorization scheme based on existing theories and research. And to operationalize these categories, we then develop a code book with definitions and instructions for how coders should apply these codes when reading documents. This step can be pretty tricky since it requires the researcher to make assumptions about a coder's prior knowledge when deciding how detailed to make the code descriptions. So here at number 2. In an ideal world, you could use this code book and code all the documents of interest that you have. However, this is often ill-advised for 2 reasons. 1, there are often a lot of documents that you're interested in, and needing to read, interpret, and categorize all of them is very burdensome. And number 2, just because you created a code book doesn't mean that others who use it will be able to interpret the same way, making replicability a concern. Therefore, instead, we usually draw a small random sample of documents, number 3 on the diagram, and then have multiple people code all of them independently, number 4 on the diagram. We then compare the coders' responses to each other and calculate inter-rater reliability metrics, sometimes abbreviated as IRR. We're now at number 5 at the bottom right-hand corner. So if the IRR is low and the coders can't agree on how to code observations, then we're back at the drawing board and we start this process all over again. However, if the agreement is high, we can then draw a large random sample of documents for the final coding, number 6. And since the agreement is high now, remember, and it's been determined that the coders are categorized in a similar fashion, we can then split up the documents in the large sample across coders so that each document is only coded once. And then lastly, number here at 8, we can calculate the summary statistics of the frequency of the codes as well as their associated confidence intervals. All right, next slide. All right, so then now that we're on the same page, our research question is, how well does ChatGPT perform deductive coding compared to human coders? And we're going to evaluate this on 2 different components, one based on iterator reliability, and 2 based on coding time. Next slide, please. So to answer this question, we started by looking for publicly available data sources that include the document text, the coded data, as well as a code book. And surprisingly, this was really hard to find that many data sets that met all 3 of these criteria, but we eventually found a couple that represented here that kind of represent different types of documents, categories, and coding schemes. Next slide, please. Okay, we then developed prompts to tell ChatGPT what we wanted it to do. Here's a very abridged version of our prompt based on what we did in this work. I'll quickly read it aloud to give you some intuition for how this works. So we started off with a technique called role prompting, where we ask the model to pretend it's something, it takes on a certain role to do the task that we're asking it to do. So we're telling it, you are a qualitative coder who's annotating news articles. To code this text, do the following. And then we give it a list of instructions, inspired somewhat by the chain of prompting technique. So we say, first, read the code book and the text. Next, decide which code is most applicable, and you explain the reasoning for the coding decision. And then finally, print the most applicable code and your reason for the coding decision. And then we tell it the format that we want it in, and we feed it the coding instructions, we feed it the documents, we give it the codes that we want it to code for, and then we ask it to return the coding decision and the reason for that decision. All right. So as a final background before we share results, I wanted to explain how we assess reliability, introduce some terminology that we'll use in the coming slides. So as a first approach, we calculate what we call the human model agreement here on the right-hand side of the slide, which is the agreement between the original published codes and the codes predicted by ChatGPT. Now, we could have totally left it there, but we felt it'd be an issue interpreting the results if the agreement was low. Was it low because ChatGPT was hallucinating and doing a poor job at coding? Or was it low for the same reason that IRR is often low between human coders, because the codes are vague, poorly defined, or too subtle? And that's why we also included here on the left a human-human agreement comparison. This measured the agreement between the original published codes and an independent coding conducted by our team using the available codebooks. So now if the human model agreement was low, while the human-human agreement was high, we'd know that that low human model agreement could be attributed to a failure of ChatGPT in conducting the task. All right, let's move on to get some results. Next slide, please. Okay, so our first major finding was that GPT-3.5, which is the model we used at the time, often coded at levels of agreement comparable to humans. So here in the middle of this table are those human-human and human model agreement metrics that we talked about. And you can see here in the green cells, there are many times when these 2 values are very close, indicating that they're potentially comparable. Next slide. However, unfortunately, this wasn't always the case. Now, these rows that are highlighted in red are categories for which the human model agreement was far below that of the human-human agreement. So while this is potentially concerning, one silver lining is that we were often able to predict when ChatGPT would fail in this way. And this is based on an approach that we came up with called the, not very novel, but the tests of randomness, where we compared ChatGPT's code frequencies to that of a random process. Our hypothesis was that if ChatGPT didn't understand what it was coding for, that it would essentially be forced to guess at random. And therefore, if the code frequencies produced by ChatGPT were unable to be distinguished from a random process, then it was flagged as being potentially suspicious and prioritized to look at first. As an example of this failure, let's look about halfway down at the individual code, the INDV, which is short for individual. And this code was supposed to be assigned if a tweet mentioned any individual person in a text, either by name or indirectly. And when we looked at ChatGPT's reasons for coding decisions on these tweets, we saw that ChatGPT was often overassigning the individual's code to tweets that mentioned groups, such as political parties or police departments. Now, its reasoning for this was that since a group is made up of individual members, then the individual code should apply, as there's individuals in there somewhere. And while I'm totally certain that's not what the original research team intended for how this code should be coded for, it does potentially illustrate a path for improvement that you could overcome by being more explicit about what counts as an individual in your codebook description. Next slide. All right, I see we have 1 minute left, so I'll try to be real quick here. These are the new results. Essentially, we also ran this now with GPT-4, and that's that left column on the right. The high level, maybe not surprising, is that when we used a bigger, better model, we got better performance. The ones that it did where that we saw the biggest performance were actually really interesting, but in the interest of time, I'm going to skip it. But if you have questions about it, let me know and we can come revisit this slide. Next slide, please. Okay, as our final main result, we wanted to compare ChatGPT to human coders based on the coding time. And what we found, maybe not surprising, was that ChatGPT was substantially faster than humans at deductive coding, especially for long documents with many categories. A nice example of this is this last row here in blue from the contrarian claims dataset, where it took human coders around 2.5 minutes to code a document. In contrast, ChatGPT took only 4 seconds, meaning that the model could code 36 documents in the time it took our human coders to code 1. However, this was a bit of an underestimate because ChatGPT not only provided a code, but also a reason for the coding decision, whereas we only asked the human coders to provide their coded response. Next slide. 2 more slides and we're done. So overall, we believe our findings have several implications for future deductive coding practices. First, based on our results, LLMs do appear to be pretty promising for deductive coding, and in many cases might even continue to get better. Second, using large language models for deductive coding likely requires us to rethink how to do deductive coding from the ground up. For one, at the very least, I think it will require different types of reporting and documentation, such as publishing your prompts in code books to support reproducibility and critique. And as a way of promoting the standard, we provide the prompts, code books, and models details for this work online. And then lastly, despite these implications, we do not consider LLMs as a replacement for qualitative coders in any way, but rather as a tool to support accelerating the latter stages of deductive coding that honestly tend to be more manually taxing and repetitive for researchers. Okay, and to finally just make this concrete, we put this all together in an approach to deductive coding using large language models that we have called LLM-assisted content analysis. Right, so now, and over here, number 2, instead of developing a codebook alone, you can co-develop a codebook with a model like ChatGPT to understand where there are gaps in understanding and interpretation. And additionally, over on the right at number 4, additionally, instead of the human iterator reliability, we can also calculate that human model iterator reliability like we did in the previous slide. And then lastly, over here, number 7, our big time saver, instead of manually coding the final large set of documents, we can these can instead be coded by a large language model. Okay, next slide. We'll skip limitations for now. Next slide. And thank you for letting me present. Any questions?
Thank you, Rob. Okay, so I apologize for allowing this session to go beyond our originally scheduled time. But if there are any questions in the chat, I can maybe bring it up quickly. If you have any questions, please post on chat. Okay, I don't see any questions, but I do have one question maybe for all panelists. And I think this was sort of the theme for this session here, was that, you know, the large language model that you guys are looking into, you know, definitely has this potential to improve our, you know, data collection and processing. But, you know, so far the results are somewhat mixed, right? That, you know, there isn't just like a single, you know, plug and play kind of thing where you can just take a model off the shelf and, you know, use it for to replace human experts that we currently have. So the question for you guys is, you know, like, are we often, it seems like, you know, sometimes we are applying these large language models on tasks that are even difficult for human experts to do, right? Is that something that we should rethink about? You know, maybe, you know, we should apply large language models for something that is a little bit more practical in a sense. Are we sort of doing the innovation disservice by sort of giving LLM the tests that are very difficult from the from the start, or should we sort of, you know, ease into sort of incorporating large language models into our production process? Any thoughts?
I can kick off really quick. I think one of the things we need to remember is there's a lot that we do that involves language, right? Whether it's writing reports, whether it's writing drafts of questionnaires, whether it's coming up with initial code books, there's a ton of things that we can use this for that make things quicker and easier, and then bring in the human element. So I think the big distinction that I've seen here is the use for it like that. Again, the same way you would use Word or PowerPoint, those kind of things. But when it gets to analytics, the analytic piece is the bridge that right now, you know, and again, because LLMs have inherent randomness and other things in them, there's going to be somewhat different. So I think it gets back to the use case that you have, fitness for use. For government work, it's not there at all. You know, if you're doing quick commercial and you need something really fast and you just want the themes, and if it doesn't really matter that the themes are slightly different, boom, you could use something like that. So again, I think you hit the nail on the head, which is you don't dismiss it because we've given it really hard tests now. I think we need to see where can it be used right now and then move forward.
Michael. Yes, Francis?
Yeah, I 100% agree with Michael. As far as just, I mean, we need to, what we're not seeing in these presentations and is really optimization of the prompting that, and yeah, I think I mean, in my PhD work, I've been doing a little bit of it with like where you do a genetic algorithm and you can significantly improve the performance. And I'm giving the work I'm doing is I'm testing on tasks which human experts find virtually, I mean, very challenging. You have to, you know, like people who are highly proficient in the field, and I bumped up the predictive results from 55% to 65% as far as, and so at 50% it was correct or not, basically. So 50% is random, 55%, but then I mean, just using a genetic algorithm to search through like 120 different prompts, and so I think there's really a lot to be gained there. Yeah, as far as like, I mean, I don't see anything wrong with giving it tasks which are beyond what humans find challenging. And on a day-to-day basis, I use these large language models for coding, for, you know, composing emails, for transforming emails, for editing emails, for, I mean, it's just, I think everybody should integrate it into their workflow. It's just a fantastic tool.
Thank you.
Yeah. I would just add on and essentially echo what the others have said. I think in terms of personal productivity use cases, there's a ton of things that you can do within survey operations, even just within your own, you know, work day that can really help speed up things that are really routine and that you don't mind giving away. Honestly, you're like, okay, less emails, I'm okay with this. I think when you're doing more analytical tasks, a big component, and this is where I think, social scientists and survey methodologists in particular probably have a lot to say about it, is just thinking about, in many cases, is there really a ground truth? And really thinking about the human benchmark. I think that was one thing that we found really useful when we were doing our assessments was, it wasn't always clear that what the model was doing was wrong. Sometimes it was very wrong, and that was obvious, and oftentimes very comical when it would do that. But other times it was very subtle when the difference is, and it wasn't always clear that the ground truth that was provided really could be a reliable measurement of the thing that they were originally trying to measure. So I think thinking really hard about, if the task that if you're asking a human to do this task, if you would expect the model to do much better than a human on it, and if there are failures, how do those failures differ than a human might, to be able to combine the efforts and the best of both worlds.
I would like to add just really like a production application. It would be like semantic search using large language models. That is really on top of in Sensei that we're working on.
Thank you all for your comments. Yeah, it's LLM is very interesting field. It's continuing to change, and like what Census is doing in terms of augmenting the language model with metadata. I think it's very interesting. Hopefully that can also improve some performance and things like that. So thank you, presenters, again for just sharing your amazing insights with us. I apologize for going over, but I can speak for that we got a lot out of this. So thank you again. Thank you everyone for attending.
Yeah.
And
thank you for sharing everything. Thank you.
Thanks for the opportunity.
Bye.